So, like many of us, I've changed my title. And what did I do here? Okay. Okay, I should not touch my laptop. So I changed my title, and in common language, we don't make much of a distinction between prediction and forecasting. And but here's a quote from Benno Gutenberg, which you can find actually later in the front of the conference room at Caltech at the Seismolab. I'll read it because it might be a little too far. This laboratory does not predict earthquakes. Specific predictions giving time and place come from amateurs, publicity seekers, believers in the occult, or just plain fools. So better not use prediction. So I switched to forecast. I'm not sure whether he meant forecasting or prediction, but anyway, we'll see at the end in which category I fall. So some years back, there was an effort made by the International Commission on Earthquake Forecasting to actually define clearly what is meant by earthquake forecasting. Okay, so earthquake forecasting is probabilistic. The objective is to assess the probability of having an earthquake larger than a certain magnitude in a certain time window in a certain area. So this is what earthquake forecasting is about. So in this talk, I will talk about forecasting seismicity rate, mostly in the context of induced seismicity. And then we'll talk about the prospect for forecasting individual events, which is a slightly different problem. So I'll start with a basic notion of earthquake phenomenology and fault mechanics for those who are students who might need that, or those like me who start to forget. Then I will move to the principles of earthquake forecasting, how we have set up our forecasting method. And then I will illustrate how this works for induced seismicity, and then I will move to natural earthquakes. So let's start with my favorite earthquake, which is the Gorkha earthquake, which occurred in Nepal in 2015. Yes, there's an animation here. So we have a lot of information on that earthquake, on the context of that earthquake, because, I mean, it's like a subduction system, except that it's on land, right? So we have stations sitting right on top of the lock patch of the main Himalayan thrust. And we had at the time actually permanent GPS stations that were recording continuously the ground motion. So the earthquake started something like 150 kilometers away from Kathmandu, so west of Kathmandu, and propagated westward. So this is an animation that is combined, that was produced from the inversion of the GPS time series. And on top of it, you have the radiation of high-frequency waves. So this is the work of Lingsen with Pablo. So what is plotted here is the slip rate on the fault as a function of time. And you see that it started 150 kilometers from Kathmandu, and then it propagated eastward, producing a very nice slip pulse. Okay. So this earthquake occurred at the down deep edge of the locked patch. So the red area is the area of the fault that is locked according to geodetic measurements. And you can see that it actually ruptured only a very small fraction of the locked area, and it's 7.8 already. So you can see that this locked patch could host much larger earthquakes. So this is a major concern, and we would like to be able to say something about the probability, for example, of having an earthquake propagating the other way in that segment that hasn't ruptured since 1500. And so there is, if you just do a back of the envelope calculation, there is energy enough to produce a magnitude 9 earthquake in principle. Okay. So that's really what the motivation for this work is. One point I'd like to make here, in the back, you see those dots, the black circles or the black dots here. These are the earthquakes that were recorded before the Gorkha earthquake during the interseismic period. These are mostly very small earthquakes, magnitude 5 and smaller, so small by I mean, compared to large earthquakes in the Himalaya. And you see that they are following the down deep edge of the log4 zone. So this is where you have stress accumulation. So it does make a lot of sense. And this earthquake is a little bigger than the average, the Gorka earthquake, but not a lot bigger in the end. Another point we can make that is interesting is that the high frequency waves were produced from the area where you have the background seismicity. So my take on that is that this background seismicity is producing heterogeneous stresses, and when the large earthquake occur, propagate through that, that's where the high frequency waves are coming from, most. Okay, so more on earthquake phenomenology. Now we're looking at the seismicity catalog of Southern California, the QTM catalog that was produced by Zach Ross. And this is a plot showing the distance in time and space between consecutive earthquakes. So you have risk scale time here, risk scale distance here. So this is a plot that has been popularized quite a lot by Zai Lapin and Ben Zion. And when you do such a plot, what you see is that you have two modes. You have one, let's start with this one. You have one mode, which are the earthquakes that are close in time and space. So these are aftershocks, and foreshocks would be included in that mode as well. And then you have this mode, which represents the background seismicity, the independent events, which can be considered as resulting from a Poisson process. And actually, if you plot the interevent time distribution for the events in that mode, you find that they follow an exponential distribution. So it's very much what you expect for a Poisson process. When you look at the time evolution of the aftershocks, you have the standard Omori law with a logarithmic increase of the number of earthquakes as a function of time. Okay. More on phenomenology, the Guttaberg-Richter law. So here what is plotted is the number of earthquakes with magnitude above the value plotted here. And as you know, we typically see a decay with a slope of about 1, typically. And the rollover here is due to the lack of detection. And here, generally, you have variability just because you have small, a small data set, so you have more variability. So you can see an earthquake catalog as a stochastic realization of a stochastic law that is represented by the PDF. So you can adopt the Guttaberg-Richter law, or you can adopt actually a tapered version of it. I will talk about it later. So one issue so why is this law important? Is because most of the work we can do is require large data sets. So we are working with small magnitude earthquake. So we want to learn from small magnitude earthquake to say something about the probability of large events. So we need a scaling. We need a relationship between what we can tell at this level and what we can tell at this level. One issue is where to end that distribution. Okay? For seismic hazard, most of the time it's not a big issue, but if you look at the probability of extreme events, if you care about, for example, seismic hazard for nuclear facilities, then you start to care a lot about Mmax. So a simple way to place a bound on maximum earthquake. First, there must be a bound, right? You cannot have an earthquake of any magnitude. At some point, the Earth would not be large enough to host them. And a simple way to do it for tectonic earthquakes is to say that the strain released by earthquake cannot exceed the strain resulting from tectonic loading, from plate kinematics, basically. And so when you actually follow that kind of reasoning, you can actually draw a line that represents the maximum possible earthquakes, assuming a Guttaberg-Richter distribution, right? On the intersection between the red line and the blue line would give you the expected maximum magnitude. So this moment conservation principle will be used a bit later in the talk. Okay, so how do we go from knowing let's say the magnitude frequency distribution of earthquakes to earthquake probability. So here I'm going to show plots that are based on the work that Ojat did recently. It was published in Seismological Letter this year. And so we're looking at Groningen here. And so this is the Gutenberg-Richter fit to the observations. You can actually, you have one realization, which is the historical seismicity. And here you have random realization. And you can randomly go away with a taper distribution and sometimes larger than expected earthquakes, right? So if you assume that the magnitudes are independent and identically distributed, you can come up with an analytical expression. So you can go to the paper by Nicholas van der Helst about that. That's going to give you the estimated value of the maximum magnitudes, which is simply the intersection of the blue line with 1 here, as a function of the B value on the total number of earthquakes above magnitude 0, okay? Or above here, above the magnitude of detection, MC. Okay, so based on that, all you need to know is N, the number of earthquakes that you have generated, the B value, and then you can estimate the expected maximum earthquake. So the maximum earthquake expected to have been observed in a certain time window during which these N earthquakes have occurred. Okay. So now if you take into account the uncertainty on the B value and on the fact that you have you're going to move randomly away from the ideal distribution, you can calculate the probability of having observing an earthquakes above certain magnitude over certain period of time. So here this is time, and here, for example, you have the probability of observing an earthquake, let's say, larger than 3.5 as a function of time. This is for Groningen. I will talk about Groningen later. So this kind of probabilistic calculation take all uncertainties into account. Okay, the uncertainties on the B value, the stochastic, and you could take into account also the uncertainties on the forecasting method that I'm going to explain later on. Okay, one word about the shape of the magnitude frequency distribution. There's quite a lot of literature on whether we should taper or not the distribution. It happens that, for example, in the context of Groningen, we do see a relatively persistent tapering of the distribution at large magnitude, and you can fit it by putting an exponential tapering at the end of the distribution. And then you fit the data extremely well. And when you look at the historical data, the tapering is very persistent throughout the period of operation. So it matters quite a bit when you start to look at the probability of earthquake larger than 3. So here you have the same calculation that Ojat did. The probability, let's look at the probability of having an earthquake larger than 4.2 by 2030. So you see that the probability is maybe 55% if you assume that you have a non-truncated Gutenberg-Richter distribution, if non-tapered. If you introduce the taper, it drops to 0. Okay, so it has a massive effect. This problem of the shape of the MFD at larger magnitude. And I won't talk a lot about it, but I just wanted to point to it as being an issue we will need to understand a little better. So when we want to forecast earthquakes, or seismicity rate first. So we need to estimate A, B, and eventually the corner magnitude if we use a tapered distribution. So we need some physics now to try to constrain those quantities, which may vary in space and time. Okay? So and the max as well. So I have my earthquake machine. Maybe not as fancy as the one that we've seen in Nice or Rome. And you can operate it only with appropriate, with appropriate head protection. Okay, and actually, we've learned a lot from rock mechanics, maybe not exactly this kind of experiment. So in a very simple system like that, of course, it's a spring and slider system. You have a periodic behavior. And on the common view is that you reach a static friction, you drop to a dynamic friction, and you get a cycle from that. Okay. And so this is more or less the elastic rebound theory from Reed. So in a system like that, it's interesting to see what kind of prediction we get from a very simple system like that. In a system like that, the prediction is that the seismicity rate is simply proportional to the stressing rate. Okay? And here the earthquakes are assumed to be instantaneous. So I will come back to that. If it's true if it's only monotonic, if you're only pulling, if you start moving back and forth, it's not true, but you can do a simple calculation to account for that. So let's now talk about the condition for failure. Okay, so we know from rock mechanics that a good approximation is to represent the failure envelope with a straight line. So this is the Moore-Coulomb criterion. So the way to assess the probability that a fault will be activated is, due to a stress change, is to look how much closer faults with different orientation are going to get from the failure envelope. Okay? So these are the Moore circles. The black dots represent particular faults. And the question is whether after stress perturbation, some of these faults might actually reach the condition for reactivation. So the continuous line would be the failure envelope for low cohesive faults. So the failure envelope goes through the origin, and this would be for the intact rock. Okay. So this reasoning led to the introduction of the Coulomb stress failure function. So which is simply a measure. If you have a stress change, the state of stress on the fault in the normal stress, effective normal stress, shear stress representation will move with respect to the failure envelope, and you're calculating by how much closer or farther away it gets from the failure envelope. So when you do that simple calculation, this is the equation you get, and you see that the term that is important is that term, the change in shear stress minus friction time the change in effective normal stress. Okay? So that quantity is typically what we use to assess whether we get closer or farther away from rupture. And we know that that works pretty well to forecast aftershocks after large earthquake. This was shown by the seminal work by Rothstein, Jeff King, and others. So this is for the Landers earthquake. Red is where the Coulomb stress was increased, and blue is where the Coulomb stress was decreased, and the white dots are showing the aftershocks observed following the Landers earthquake. Okay, so I already said that, but if we assume that all that happens is when you reach the condition for failure, you have an instantaneous rupture, then you expect in that system that the seismicity rate R over the background rate will be proportional to the stressing rate over the background stressing rate, okay, for monotonic stressing history. And so, for example, if you have a ramp in stress, you expect that you're going to have an instantaneous increase of the seismicity rate, uniform, and then it drops to 0. Okay? So we know that this is not a very satisfying way of representing the rupture process, simply because we see very little correlation between earthquakes and tide. If the earthquakes were instantaneous, they would happen only at the time of the peak Coulomb stress every day during the time. They would be extremely synchronous with earth tide, and they are not, right? And so this point was made, for example, in that nice paper by Nick Biller and Lochner from 2003, where they say, okay, we have a good explanation for that. It comes from the nucleation process because it takes time for an earthquake to nucleate. And rate and state friction actually does a good job at leading to a representation of the nucleation process that could explain this thing. So I won't go into the detail of earthquake nucleation. You have excellent papers on the topic that were actually written by Pablo Ampuero with Alan Rubin. But I will explain the principle of the method that Jim Dietrich proposed in 1994, actually to relate seismicity rate to stressing rate. That's what we're going to use with some caveats, with some modifications. So the method is based on rate and state friction. I will not repeat what we've heard already. Here we are using the aging law. This is what Dietrich did in his paper. And as you know, if A minus B is negative, and if the system is not too stiff, then you can get a slip and stability. And the stiffness relates to the size of the fault patch, so you need a critical size for an earthquake to actually nucleate in this model. So in his 1994 paper, which was actually revisited, an excellent paper by Elias Amisson and Paul Segal from 2020, he assumed that he has a population of fault that is above healing. So above healing means that term here can be larger or smaller than 1. If it is smaller than 1, then you see that theta is increasing in proportion to time. Friction is going to increase. So this is the healing process that Chris was talking about. If that term is larger than 1, the fault is weakening, and the fault is self-accelerating, and you can get an earthquake. So this is the slip evolution, the slip rate evolution. When you are above healing, you see that the fault is accelerating until it goes to a singularity, and so that's the earthquake. So if you assume that you have a population of fault above healing, and that you apply a certain stress history represented by the Coulomb stress, so here delta S is the change of the Coulomb stress as a function of time, you come up with a relatively simple equation. So here is the background, is the small r is again the background rate, r is the seismicity rate at time t, and here you have a simple expression, so the exponential of the change of Coulomb stress over a sigma, and here you have an integral that actually introduces some memory effect. So let's look at what is the behavior for a population of fault that is submitted to an instant change of Coulomb stress. So here you have, let's start here. So here you have an example of a fault that is initially above healing at a relatively fast rate. You apply a step in Coulomb stress, and what happens is that this branch disappears, and this branch is moved to here. And so the earthquake happened much earlier. So you have a time advance, okay, that you can calculate analytically. And you see that this time advance is going to depend on the slip rate at the time the perturbation occurs. So if you now consider a fault that is starting at a much lower slip rate, and you apply the exact same Coulomb stress change, the time advance now is massive. Okay? So now if you imagine, as what Dietrich was doing, that you have a population of fault with a very ad hoc distribution, a logarithmic distribution of initial velocities, this population would have produced a uniform seismicity rate, right? And when you apply the same step in stress at a given time, you produce clustering, okay? And it happens that actually you get something that looks very much like the Omori law. So this is one reason also this model is quite popular, is that it can explain aftershocks relatively well. So if the shocks the events are still independent from each other, but they were all triggered by domain chart in this logic. One point I wanted to make about this logic, it's very different from ITAS. Here, you have a finite population. Let's say that you have a population of fault in your medium. This population is finite, and you are changing the time at which the earthquakes are happening. Okay? It's a time shift. In ITAS, you are adding earthquakes, and it can blow up, as you probably know. So it's a very different process. Now, the law we are using in what I'm going to show next is a revision from the logic of Dietrich, and that is needed when we deal with induced seismicity. Very often, earthquakes have been induced in areas where tectonic has been quiet for a long period of time. That would be the case in Groningen, and we'll talk a bit about Oklahoma. And so in that case, you cannot assume that you start from a population of fault that were on their way to rupture. Okay, so the population of fault might be below healing. You might be in a healing mode. So it turns out that when you take that into account, it makes a very simple simplification to the equation I already introduced. It introduced a threshold. You need the Coulomb stress to reach a certain threshold to induce seismicity. So now, if we go back to that thought experiment where we have a ramp in stress over a limited period of time, the thing that happens with this model is that first there's a delay. The earthquakes don't start right away when the perturbation is applied. On next, it's not, you don't reach a plateau. You have actually a smooth evolution of the seismicity law, and you have a Omori decay when you stop the perturbation. Okay? Okay, so let's move to application to different contexts. We'll start with the context of gas extraction, and then we'll move to injection at different rates. Oklahoma, it's relatively slow rate, and we'll talk about hydraulic stimulation for EGS, which is a very different regime. So Groningen is quite interesting. They started producing gas from that field in the Netherlands in the 60s, and it has induced a reduction of the pressure of the gas in the reservoir. So the reservoir is about 200, 300 meters thick at a depth of about 3 kilometers. And so this is the history of the production at Groningen. The blue line here is showing the rate. It will come later in the talk. It's important. You can see that it's very seasonal because they produce more gas in the winter than in the summer. And so you see the wiggles here, so you will see that it matters. Seismicity started in the 90s, so you have a lag of more than 20 years in that case. And it started exponentially and then slowed down a little bit. So the objective is to try to develop a physics-based model that can explain the observations. Oh, I didn't comment on this plot, sorry. So here, this is the subsidence. Due to the poor pressure of deflation at depth, the land is subsiding, and it has subsided by more than 40 centimeters. This will come in the story because that gives us information about the geomechanics. Okay? So we've been using measurements of subsidence to calibrate the geomechanical model. So the modeling, the details are a bit complicated, but the principle is simple. We start from the operational data. We have the flow rates, the extraction rate at the various wells. We have the pressure data. So we develop a reservoir model that represents pore pressure diffusion in the reservoir. Okay. So next, we use the pore pressure diffusion model to feed the geomechanical model. So we're going to calculate the surface deformation and actually stress changes in the whole volume. And this model is calibrated using the geodetic measurement of surface subsidence. And then we use the geomechanical model to calculate the Coulomb stress changes. And here we have the seismicity model, so the equation I just introduced. And then you can forecast the seismicity rate. Okay? And then you can introduce uncertainty quantification and compare and play the game, you know, testing the quality of the performance. So very quickly, this is the reservoir modeling. We fit the data. I mean, the pore pressure drop is massive, up to 30 megapascal. And we fit the observations by about 0.6 megapascal on average, which is actually something similar to what the operator has. They have a fit of about 0.5 megapascal. Our model is way simpler. It's a 2D model, in effect. It's a vertical flow equilibrium model. So, okay, so now we have the pore pressure distribution in the reservoir as a function of time, well calibrated from all the well data. We calculate the deformation at the surface and in the bulk using a semi-analytical approach that was developed by Kufshinov. So it's based on the theory of a nuclei of strain in an elastic medium, and you do an integral of the analytical solution over a finite volume. And he came up with nice equations where you can represent the effect of pore pressure changes in any polyhedral volume. So in effect, what we are doing is that we are discretizing the reservoir in cuboids, and we place the limits so that we fit the faults. I didn't say, but we have access to seismic imaging. We see the faults quite nicely in those data. So it's a way to take into account the faults offsetting the reservoir. It's going to matter quite a lot. Okay. And then what we do is that we use the transverse subsidence to calculate the compressibility, how much change in thickness of the reservoir you get for a given drop of the pore pressure. So it's a relatively simple quantity. It's uniaxial compressibility. Okay, so then you can calculate stress changes in the medium, and that's quite going to feed the seismicity forecast. Yeah. Maybe I'm missing a plot, but anyway, when you calculate the Coulomb stress changes, what you find is that the Coulomb stress changes are going to be maximum where you have offset of the reservoir, and they are maximum actually at the offset and at the top at the bottom of the reservoir. Maybe I will have the plot later, so I put it here. Anyway, so these are the leveling data. The leveling data here, the GPS data, the INSAR data that we use to calibrate the compressibility. So we have a relatively good model of the compressibility. It's variable in space. It's not completely uniform. And once you do that, you can actually fit pretty well the observed GPS. So this is one GPS station here that is showing the seasonal fluctuation of the land surface. You have INSAR on the blue line that is a little before actually is the flow rate, the local flow rate. Okay, and there's an offset just because of the time needed for pore pressure diffusion. Okay, so seismicity. Seismicity, if you look at the depth distribution of hypocenters, this is work that Johnny Smith did some years ago. You find that you have a peak in the distribution right at the top of the reservoir. So the earthquake might be in the cap rock or very close to the top of the reservoir. This is debated. The thing is that it's very peaked. It's a very narrow range of depth, which might explain why we have tapering. So next, what we do is that we calculate Coulomb stress changes at this level, where we have the peak distribution of seismicity. And then we feed that to the seismicity model, and we do a MC-MC inversion of the model parameters. So this is the work that Ojat did. And so again, you have the equation here. And here, he used half of the catalog to actually determine the model parameters, so for training, and the other half is used for validation. What is plotted here in blue is the observed seismicity every year, and in red here are the prediction of the model from the MCMC inversion. And in black, this is the range that is estimating from his uncertainty quantification method. So you can see that it fits the observation pretty well, and it's well validated for the second half of the catalog. The peak, the decay of the seismicity rate is simply because at some point they decided to actually decline the prediction because of the earthquake, and now they have completely stopped because of the earthquakes. Here you have the observed distribution of seismicity, and this is the prediction from the model, so it's doing a relatively good job, simply because we have this offset in the reservoir that are creating zone of stress accumulation. If the reservoir was completely uniform, you would have a rigid subsidence of the land and nothing would happen. Yeah.
Really quick question. Is the nucleation duration of 7,000 years? No.
Okay, so good point. So I'm going to talk about that. This is the nucleation time for earthquake that would happen under tectonic loading. But once you do the perturbation, you have, TA is A sigma over tau dot, the stressing rate. So the stressing rate is suddenly many order of magnitude larger. So this nucleation process is going to be accelerated and by many order of magnitudes. And it turns out that it's more the order of a month or something like that during the perturbation.
Another clarification question. So you don't take into account clustering, right? It is individual nucleations rupturing independently.
Yeah. That's right. So it turns out that when you do an analysis of clusters in that catalog, there are very few aftershocks, maybe 10%, something like that. So in principle, what we do is that we remove the aftershocks, we calibrate the model with the declustered catalog, and then you can bring back, if you want the declustered, if you want to do a time-dependent earthquake forecasting. Yeah. But to calibrate the model, you need to indeed remove the clusters.
Jeffrey, one other clarification. The catalog is really this boxy? It jumps up and stays for several years at one level?
It's from one year to the other. Yeah, it does that. Yeah. No, this is this is not so unexpected. These are relatively small numbers, right? So these are just the random fluctuation from the Poisson process. Yeah. And when you compare, actually, there's a discussion in Ojat paper. It fits pretty well the expectation for a Poisson process. Yeah, these variations. Okay, so seasonal variation. So we've seen that there are seasonal variation of deformation, and it's important for us because it's going to help nail down the nucleation process. If you just look at the seismicity rate per year, you're not going to see the nucleation process. You need to go at a sub-annual scale to see it. So how do we see it? Here you have a plot that was actually introduced by Schuster in the 19th century, who was interested in the correlation between earthquakes and tides. And the principle of that plot is that you make a step, so time, you go run the clock in 1 year, here. And each time there's an earthquake, you make a step away from the center. Okay? So if the earthquake happened randomly around the year, you go back to the origin. Okay? If there's a seasonality in the seismicity rate, then you're going to drift away from the origin. And you see that you're drifting, so each small circle, each wiggle is a year. And you see that you're moving from year to year away from the origin. So there is a seasonality. It's not a very strong seasonality, but there's a very significant seasonality. The probability of drifting that far away from the origin by chance, if it's a Poisson process, is only of 0.1%. Okay, so it's a very small probability that it would be that we would have this drift by chance. So there's a significant seasonality of seismicity. So we can check, is our model producing the correct seasonality of seismicity? Okay. So before we show our model, I show what we would expect for a standard Coulomb model, where we assume that the earthquakes are instantaneous. This is where we should be. We should be here, so we should have a much stronger sensitivity to the stress changes, and we don't have the right phase. It should be in January, not in March. Okay? And with our model, this is what we get. Okay, so we have the right response to the seasonality, and we have the right phase. Okay, so this is not completely surprising because when actually we do take into account the seasonal variation of stress in our model, so it's in the model. If we remove the seasonal variation, if we kill them, we can fit very well the observation. So the green lines are showing a model where we actually remove the seasonal variation of stress and calibrate the model to fit the annual rate. You can fit very well. But when you do a forward prediction, it's all over the place because the model is not as tightly constrained as when you take into account the sub-annual variations. Okay? So it helps quite a bit. And you see that this model would not produce, a model calibrated only ignoring the annual rate would not produce any seasonality. The nucleation process is too small. It's too long, sorry for that. Yeah, so the order of magnitude is 0.1 to 1 year for the nucleation process because of the perturbation. Okay, one quick note about the magnitude frequency distribution. This is work by Yuri Tamama, which just came out in Geophysical Research Letter. And what she observed is that the magnitude frequency distribution is dependent on the stress rate. I will not go over the detail of that, but if you bin the catalogs between earthquake happening at high stress rate and earthquake happening at low stress rate, you find that there's a significant difference. So the blue is at low stress rate, the orange is at high stress rate. And the gray are random catalogs where you shuffle all the earthquakes around. And you can see that you are at the extreme end of what you can get by reshuffling randomly the catalog. So it's a very significant signal. So earthquake have a higher time to grow to larger magnitude when you push them too much. Okay? If you push them less, then they can go more easily. I don't think I think this is probably very specific to induced seismicity because you're pushing a system that is not already self-organized. You're pushing it and you get this kind of behavior. Okay. Okay, so now I have too many slides. This is just to show that the model is fitting the MFD relatively well. The tapering is persistent. And so when we look at the expected maximum earthquake at a given time, we always overestimate the magnitude. So we have a conservative forecast in that regard. Okay, let's move to Oklahoma. Same framework, so I will go fast. And except that now it's injection of wastewater at the top of the basement at a depth of about 2 kilometers. And the earthquake happened this time in the basement. So same principle as for Groningen. Actually, what we are looking at, I didn't say it, it's pore elastic stress changes. There was no pore pressure diffusion to where the earthquake were happening in what I've shown earlier. So we're doing the same assumption here. We are neglecting the idea that there would be diffusion of pore pressure in the basement. There's a delay between the injection rate and the seismicity. The seismicity rate picks up after the injection rate. So same thing we do. We fit we have a reservoir model, and we try to fit well the seismicity rate as a function of time. And you can see that you can fit very well the time evolution. So this is based on Coulomb stress calculated at the depth of about 6 kilometers. The parameters, surprisingly, are not very different from what we get for Groningen. We get, I didn't insist on that. The threshold is very important. We had 0.3 megapascal for Groningen. It induced a delay of about 30 years. Here it's 0.5 megapascal, and it's a more brutal operation here. And the delay is of the order of 2 years before you really have the seismicity picking up. Okay? So the model seems to work in extraction and injection at relatively slow rate, and now we are we are going to injection at much faster rate now. That's for hydraulic stimulation that took place near Helsinki in Finland. And they injected at a depth of 6 kilometers. And here you have the seismicity catalog. It's a complicated schedule. I will show a plot earlier. They had 5 stages of stimulation. And as a result of that, you don't have the typical diffusive pattern that you would see in injection experiment. The red line showed what would have been observed for a diffusive process if they had injected at a constant rate, which is not what they did. But it's just for reference. We'll see that plot again later. So the earthquake happened typically a few hundred meters from the point of injection. So yes, an interesting point to make. So this is the schedule. The orange is the flow rate as a function of time. So they go to a certain level, they stop, they call that a shut-in, they start again and so on. And they thought that this process actually would optimize the stimulation while mitigating the risk of earthquakes. Maybe Ioannis will say a word about that later. But at shut-in, you have a nice Omori law. Clearly, the Omori law we see here has nothing to do with the nucleation process. It's the pore pressure diffusion. Just to say that there's not a unique way to get something that looks like an Omori law. So we use the pressure data to calibrate the hydraulic property. And then you can calculate the expected seismicity rate as a function of time. First, using a Coulomb model, instantaneous rupture. You can fit reasonably well in time. It's not perfect. It's not too bad, but in space it doesn't work. You have the earthquake going far too far ahead. Once you introduce nucleation process, then you can fit the data much better, both in time and in space. And actually, in that plot, this part was used to train the model, and this is all a forecast. Okay? So only the first stage was used to calibrate the model parameters, and you can see that it predicts pretty well what happened next. Okay, so again, you get ad hoc parameters. There is no threshold here, simply because the pressure went up to something like, they increased the pressure by 80 megapascal in a couple of hours. So the threshold was passed in the first minute or so. So yeah, this is a very brutal operation. One point that actually Pierre Romanet was making also in a poster earlier this week, we do see something that, this is a model prediction. For 2 different values of A in the rate and state model, you see that it changed the apparent diffusivity of the earthquake pattern. So clearly, the diffusive pattern of seismicity is not only controlled by hydraulic diffusivity. It has to do with the nucleation process. The seismicity lags behind the pore pressure increase. Okay? So now the earthquakes are driven by the change in the pore pressure. That's a big difference from what we've seen so far, where it was pore elastic. Still works. Okay, so let's talk about natural earthquakes. I'm going to speed up a little bit. Natural earthquake, it's more tricky, but we'll see what we can say. First, how can we use geodetic strain to forecast seismicity rate in space, not in time? In time, it's more difficult because you would need to capture temporal variation of stress changes, which is easy to do with induced earthquake. That's why I started with induced earthquake. For natural earthquake, it's more difficult. So let's look at the India-Asia collision zone. Here you have the seismicity catalog over, I don't remember, 20 years. This is geodetic measurements of ground displacement relative to Eurasia. You can calculate the horizontal strain tensor, the principal duration of the horizontal strain rate tensor, compared with focal mechanism. They are about the same. They're very closely collinear. So these are the P and T axis, and when you compare the two, they are so close that you can actually take the strain rate, the second invariant of the strain rate, as a proxy for the Coulomb stress changes. Okay? So that's the difference with what we do with induced earthquake. So we use the strain rate. So you can calculate the second invariant of the strain rate, and you find that there's a very strong, strain rate along the Himalayan arc, and you can see some of the faults in Asia popping out. Of course, as resolution is increasing, those faults are going to be more visible. So with more INSAR data, this could be probably improved. And then what you can do, you can actually stack the earthquake happening at a certain bin of strain rate. Okay? We've seen that to first order, we expect the seismicity rate to correlate with the stressing rate. So we expect the seismicity rate to be proportional to the strain rate if we have a Coulomb model with instantaneous rupture. And this is actually what we observed. So here you have the magnitude frequency distribution of earthquakes in different bins of strain rate. Red is high strain rate, blue is low strain rate, and it's a nearly linear correlation between A, so the mirror earthquake above the detection level, as a function of the strain rate. Okay, so simple. What is important here is that you can use geodetic strain directly to inform a forecast model, and it makes it way easier than traditional techniques. Mmax. I've used Mmax in different settings, so maybe it's a bit confusing. Let's talk about the maximum possible earthquake now, not the maximum earthquake observed in the time window. I said earlier that it must be bounded. The distribution must be bounded because you cannot release more energy than what is coming from the collision between India and Asia. So if you apply this moment conservation principle to in each area of strain rate, in each bin, you find a very strange observation that because this is linear, the expected, the maximum possible earthquake to balance the moment conservation is uniform. Whatever the strain rate, you should get a maximum earthquake of the order of 8.7 when you do that. Okay? I think it makes sense for the Himalaya, but I mean, we can go to stable in India or other places. It's probably improbable that we get, I hope it is very improbable that we get 8.7. This is just to point to one limitation of what we are doing. We are assuming, in all I've shown today, we are assuming that the ratio of geodetic strain to strain released by earthquake is constant. When you go to very low strain rates, you have other processes which are releasing the strain that are not taken into account. That probably matters. Yeah. So that would affect the end of the distribution. All the rest is fine. Yeah. Okay. What can we tell about the prospect for an upcoming large earthquake in the Himalaya? Well, this is the same kind of reasoning based on a detailed coupling model, but I've shown earlier was a little more coarser. And you also find when you focus on the Himalaya, use a coupling model, you find that you need a magnitude 9 earthquake every about 1,000 years. Okay? In the Himalayan context, it might be possible, and so we worry about the possibility of having a very large earthquake in central part of the Himalaya where no earthquake have occurred for many centuries. So what can we tell about the probability of a large earthquakes? Now trying to forecast individual events. That's a more tricky problem. Here I'm showing briefly Sumatra just to show the difference between a continental setting, the Himalaya, where you have nearly uniform locking, and here you move to a subduction zone, and here it's very patchy, and we've seen example of that in many talks during the week. There's a fundamental difference. Probably it has to do with the fact that you have a lot more clay. You have this subduction melange that can creep, produce pressure solution creep and so on, which you don't have in a Himalayan context. I'm not sure what's the right answer, but it's important. So in the Sumatra context, we can also test. So we have a relatively good model of interseismic coupling. We can test the moment budget, and we can actually use the coral data. This is work that was done by Cargèse's group to actually track the time history of past ruptures. So here, this is the return period of very large earthquake, 8.5 or so, based on the coral data. This is based on the seismicity catalog, and this is the expected max based on the moment conservation. All fits relatively well in that case, so it shows that the logic of the moment conservation in a context where we have quite a lot of information does work. Okay, so I suspect that in the Himalayan context it works also. So based on the coral data, I'm not showing the record. You've seen some. Actually, Fabio has shown some examples. You can actually produce a model here of sleep deficit and sleep release over a century. What you find when you do that is that the interseismic period is relatively stationary. It does vary, but not a lot. The earthquakes are extremely variable. And you tend to see that the earthquakes are certainly not Poisson process, and they are not either periodic. They tend to cluster, so you have interaction between those earthquakes that are creating difficulty for their forecasting, but also an opportunity. Each time you have an earthquake, it's going to impact the stress field on the megathrust. Because faults are always creeping, as Chris was saying, there's an information in instantaneous model of interseismic coupling that can, in principle, be used to assess how far we might be from a large earthquake. So I had one last slide, which is about slow earthquakes. So what we see in Sumatra, you see the exact same thing for slow earthquake. If you look at Cascadia, you do have adjacent segments that sometimes rupture together, sometimes independently. It looks like you have some sort of segmentation. So this is the work that Sylvain Michel did some years ago with Adriano Gualandi. And Adriano actually has used this catalog of slow sleep events to test the predictability. And what he found, I won't go into the detail of that, is that they are indeed predictable. It's chaotic, but it's a deterministic chaotic behavior, and they can be predicted about 2 weeks in advance. OJAT has tested the predictability of slow earthquake now in numerical simulation that were tuned to do something similar to what we see in Cascadia. So this is catalog. This is the history of strain strain release and strain deficit as a function of time. So you see that it's quite chaotic, and you can talk to him. And it turns out that in this system, knowing just the information on the fault at one time, the slip rate on the fault at a given time, you can actually forecast the earthquake. So it tells you that there's an information at a given time about what happened in the past that can give you a prediction that is pretty good in terms of the location and the time of the ruptures. So I've put too many slides, and I should stop there to take your questions. Thank you. Okay, so this is a slide I skipped. So so here you have a probabilistic seismic hazard assessment based on the geodetic strain rate. We use the strain rate, we calculate the seismic rate based on that, and this is the map, and this is what was produced by GEM, which is including a lot more data. It's been, many years to produce that, and they are nearly identical. Okay, so, and this is a time-independent hazard assessment. That's the probability of the PGA exceeding certain level in a window of 30 years, right? But this window of 30 years is not specified, so it doesn't take into account the seismic cycle. Okay? It's time-independent.
Could you go back to the slide where you say lower velocity loading leads to larger magnitude events? I think that's what you said.
Yes.
For the
Yeah.
So do you have a physical mechanism for this?
Yeah, so your mechanism could work. Thank you for asking the question. Okay, let me show the slide. It was earlier. Okay, here we are. Sorry. Yeah, so what we see is that the B value is larger at higher strain rate, right? So it seems that the earthquake have a higher time to grow. So I think that if you imagine that you have rate weakening and rate strengthening patch, the rate strengthening patch have more time for stress to build up when you're perturbing at a lower rate, right? So when the next earthquake happens, the stress level in those rate strengthening might be a little higher, so it makes the next earthquake easier to grow. That's a possibility. I'm not too sure it's the right explanation.
Sorry, there's a queue of 3 more questions, so let's maybe we can begin later.
Okay, we discussed that at the break, but yeah.
Thanks for a very interesting talk. So my question is about the aseismic sleep induced by fluid injection. So, in some cases, like in observations and simulations, we see that you have a small stress perturbation. It causes a lot of aseismic sleep first, which trigger the earthquakes. So how do you think about that in terms of forecasting of seismic sleep?
Yeah, so it exists. It's been observed in many settings, and it's not included here. So here we are assuming that the stress perturbation produces earthquakes all the time. This rich model is ignoring completely the fact that at some point you may reach the condition for conditional stability. So there should, but what is strange is that it's not a first order effect, for example, to predict the seismicity at Ottaniemi. We see it a little bit, so there's a work that Theo is doing on that, but it's a second order effect. When we do a simulation, you put actual fault of finite size, not point sources. You do see this effect very clearly, right? So, but it turns out that the fraction of seismic to a seismic is not changing that dramatically. But it could be included in that formalism. It's one step further.
Really nice talk. Thank you very much. I want to ask a little bit about the phase delay between the stressing rate and the seismicity, and thinking in particular about the way oscillatory stresses induce slip. And as you well know, the theoretical work, I'll say the original work by Perfettini and others, and then the laboratory work, shows very clearly that the critical resonance frequency depends on all the parameters, and not just the friction parameter A. It depends on the friction parameter A minus B, and also has the critical slip distance in it in a way that's not very hard at all to understand. Because if you drive the system at high frequency and it doesn't accumulate any slip, then nothing can happen. So I'm wondering if you ever, like in what you did in Groningen and other places, did you run into that in any place? Or
Yeah, so the idea that we have a resonance, we don't see it. The signal variation that we have is not related to that resonance effect that Ugo Perfettini. Well, it could be there, but you would need to tune the fault patch to have the right properties so that they would resonate at 1 year, right? And we don't see in the data any evidence that we have such a resonance. It can happen, but when you take a population of fault of different sizes, I think it's going to smooth out this signal. Yeah.
Thank you, Jean-Philippe. In the last part of the talk, you talked about the predictability horizon for the slow slip events.
Mm-hmm.
I think so. Adriano finds 2 weeks.
Yeah, other
we
line.
found a couple of months, I think, from the tremor signals for the same slow slip events. How do you think this scales when you consider faster earthquakes?
Yeah.
Can we learn anything from that predictability horizon to big earthquakes?
Yeah, exactly. I think that's the direction of Ojat's thesis. So I hope he will give us an answer in a few years. The problem is whether this horizon scales with the duration of the interseismic or scales with the duration of the earthquakes, and it goes opposite ways. And I don't have a strong opinion on that. So the way we're trying to address that is to run dynamic simulations, like he has shown. We started with slow earthquake because it's easier, and we can also verify with what we're doing for what we observed at Cascadia, and we'll see what happens with the more dynamic simulation. Yeah. I bet we are going to lose the predictability, but I'm not completely sure. Yeah. I mean, the horizon is going to shrink, I suspect. But
because you did an experiment already with the simulation of displacement from this poster, right? To make a forecast of slip. And what's the assimilation? The time of assimilation is extremely important in order to not assimilate plate noise. So did you need to actually make it very short, or very often assimilate the data, or longer time spans will be fine?
well, you want to answer, Ojat?
For
Yeah.
instance, we use 5 days daily simulation.
Okay.
Yeah. But in terms of predictability, I think that don't have the clear answer that how does it scale.
Maybe that's discussion that we can continue at the coffee break. But yeah.
Let's when we walk down to the cookbook.
Yes, so we'll give instructions because it's something inside. So there are a few people who have to leave.
Yeah,
So it's Gina-Maria Geffers.
sure.
Okay. Good. And then let's see. I just want to let you know what's the new. So it's 15 minutes, right?
Yeah.
No, yeah.
I'm hoping I'm going to be even less than that.
Okay. Yeah. Don't rush. You should take your time. So okay, if you start, let's say we start in 1 minute. So then we'll do 5 past.
Okay.
Okay, let's stick to the schedule. Our next speaker is already ready.
Ready.
So our next talk will be given by Gina-Maria Geffers, and the title is Frequency Size Parameters as a Function of Dynamic Range.
Good morning, everyone, or those who are still here or have come back. It's very nice to be here. I'm Gina. I'm currently a postdoc at Lawrence Livermore National Lab, and I've been waiting all week to use this thing. So I was going to talk a little bit about what I did in my PhD, which I graduated from a couple of years ago, and that was specifically thanks to a good introduction from Jean-Philippe. Very easy for me now. I was looking specifically at Gutenberg-Richter distributed data sets, or those which are not Gutenberg-Richter distributed, but tail off, have a taper, and that basically we shouldn't just assume that the data sets we look at are necessarily purely Gutenberg-Richter distributed. And the problem we have is we assume that normally, and then we end up with lots of biases, especially in things like the magnitude of completeness, and in particular the b-value. So one of the things I was looking at was the biases in b-value and why they bias to high values, both in data sets with few samples, so few events, but also dynamic range. So we titled dynamic range as the range between the maximum and the minimum magnitude. And for example, we can have, for example, 1,000 events in only one of these, and only one order of magnitude range. Or we can have 1,000 events in 3 orders of magnitude range, and we could get entirely different results for the b-value. So in synthetic data, which is what I'm showing here, we found that both the mean magnitude of a data set and the b-values converge to perfect asymptotic limits, which we can see here. So this is actually from a paper that I published during my PhD, and these equations show that this is exactly what happens. Of course, in real data, that's not necessarily the case because we have a lot more uncertainty. And also that b-values are super high when there is very little dynamic range, even if we might have more than the rule of thumb number of events. That said, I've listened to a lot of really cool talks this week, and I actually want to talk about something that is not the ever-continuing discussion on MC and b-values. I already asked Anthony to change my talk title like 3 times, so I thought I'd try and honor it with like 1 slide. But what I actually want to talk about is forecasting induced seismicity in operational settings. So this is some of the work I do now, where we try and use existing models, physics-based, statistical, hybrid, machine learning models that are also applied in natural seismicity, tectonic seismicity, to forecast. So I have a statistical background, so I'm looking at statistical models to try and forecast induced seismicity specifically in carbon storage sites. So this is a data set I've been looking at for the last year or so from the Illinois Basin Decatur Project, which is a demonstration CO2 storage site in Illinois that was ran between 2011 and 2014 and had a goal of injecting 1 million metric tons of CO2 into a saline reservoir. They did a really good job. That's why a lot of us now use this data set. All we can see on here is all of the events and their magnitudes. The ones in green are below the magnitude of completeness, just for reference. The ones in black are above the magnitude of completeness. The red line is the cumulative number of events across the entire time period. And then the wiggly white line is the average pressurization rate, so the pressure change in time of the injection. And you can see, so the injection actually only happened for 3 years and then was stopped, and seismic monitoring continued, so we can still see a gradual increase in the cumulative number of events. Specifically, I've been looking at something called the seismogenic index model, which is a statistical model defined by seismotectonic features of a region. Originally defined by Shapiro et al., it had literally no information on the injection, the pressure. Then a modified model by Langenbroek et al., which has been changed a few times, came out, and that includes the pore pressure. Or it did include the pore pressure. We've changed it to include Coulomb stressing right now. So all this model does, it takes the number of observed events in an area or a grid cell. This is the sum because we're looking up to a certain time period. So we're taking all the data from the start up to a certain time period. So this is all we need is a number of events. There's no other information that goes into this. And the pore pressure, which we use to calculate the Coulomb stressing rate. In this case, we assume stressing rates. We assume normal and shear stress because that is the best guess we have. We actually use the ones that are used in Oklahoma and Kansas. Even though this is wildly further away, we assume that all of like the interior cratonic basin kind of has similar stressing rates, which is probably not true at all. And then we use B and MC, which are the Gutenberg-Richter parameters, to calculate a scalar value, which is the seismogenic index, which we can then plug in here to calculate the seismicity rates. Why do we care? Well, we don't want to end up with another situation like Oklahoma, where we just keep putting stuff underground, and suddenly we have, not that suddenly, but fairly suddenly we have magnitude 5 events. Traffic light systems are generally all retroactive, so ways of kind of modulating what you're injecting, how much you're injecting, depending on what earthquake magnitudes you get. And so far, actually, we have not really seen any large earthquakes in carbon storage sites around the world, but there have also only been a handful kind of projects that have been injecting a decent amount of CO2. To really combat climate goals and reach them like globally and nationally, we need to start injecting a lot more CO2 underground. So we need to make sure it's safe in different areas, leakage, caprock failure, and of course earthquakes, because we don't want anything that might confuse people, that might be felt, that could pose damage or anything else. And because we care, we have Orion. So Orion is our open source toolkit that we've been developing for, well, a good few years now. It was officially released last year. It's a pure Python pip installable package hosted on GitLab. And it's made to understand the seismic hazard at a specific site. Originally, it was created only for operators. That was our goal. But we have now actually got options for all types of end users depending on your background. So basically, if you use it, there will be a startup wizard. It will ask you, what kind of background do you have? What type of user are you? And depending on what you say, more or less options might be available to you to use. So the main, very basic things that go in is you need to have at least 2 data sets that go in. One, which is the earthquake catalog, and one, which is the pressure rate or injection rate. And then an internal TICE model can compute pressure rates. Then we currently have 4 working models in it. This is all work in progress, and we're continually improving them, improving the parameters. But we have the Coulomb rate and state, we have the rate and state ODE model. On the physics side, we have the seismogenic index model, which I just very briefly explained. And we have one machine learning model, which we just introduced fairly recently. Together, all of these, we create a weighted ensemble model that is basically meant to be the best version of the forecast. So all of these separately bring out temporal and spatiotemporal forecasts, and then this one does as well. So these are just a couple of screenshots of what Orion looks like, basically. We have a few tabs, so this would indicate that the person who's currently using it is a lay user, I would say. If you're a very specific user, you have a background, there will be more tabs. You're going to be able to upload a reservoir model, a geologic model, well information, all kinds of different things. So over here, we have the spatiotemporal seismic rate forecast. If it's purple, that means we're forecast to have higher number of events. All of the dots, by the way, are just the earthquakes above the magnitude and completeness that we've observed. And then over here, we have a probability of exceedance plot, which currently is above a magnitude 2, but that too is customizable, so you can choose whatever magnitude you want. And then we have some visualization of data of the earthquake catalog. This actually, I think, is a slightly older or buggy plot, because you can see that the best fit line doesn't even hug the data. But we have some information on the B-value, the time series, and very poor variation right now. This is probably the most important plot. So we have the temporal rate forecast ensemble down here, where the white line is the catalog of the Illinois Basin Indicator project. This has been like our calibration data set that we use to make everything. Then we have the SI model, which I showed in green, which we can see does a good job at the end. So it basically perfectly retrospectively forecasts the number of events we're expected to see at the end of injection. Of course, it does a fairly poor job at identifying clusters, et cetera, because there's no information at all that goes into it regarding these. So that's more for the CRS model, for example, which does a much better job, although this one is still currently very much work in progress. We're trying to modify it. And then up here we have a bar plot and a dial plot to basically show the probability of exceedance in an easy way that, for example, operators or someone who doesn't have any background in it could understand. So they could read this and say, oh, okay, we have a 10 or 20 or 50% chance of exceeding a magnitude, whatever, within the next 100 days or 200 days or whatever it is you're trying to find. So all of these values can be changed specific to your needs. Well, this is already my last slide. So this year has been actually a huge boom for Orion. We've been to a lot of conferences, and we've tried to get a lot of people to try it, download it, whether you have experience in induced seismicity or not. It's kind of a fun tool just to run and try. We really appreciate the feedback we've been getting, because we're just trying to improve it constantly. We're trying to include more models. There's going to be, so I'm currently working on ETAS to be included. And then also we're constantly updating our model parameters. So even though the Illinois Basin Indicator project was the data set that we calibrated everything on, we're now Also trying it on the Delaware Basin in Texas. Actually downloading Orion comes with 4 built-in examples, which are Illinois, Cushing, Oklahoma, there's a California example, and there's one more which I can't remember. So we really want to make sure that this works on different types of operations, not just CO2 storage sites, and different regions, geographically, geologically, basin scale, regional scale, etc. One of the main things we keep running into, of course, sadly, is that we don't really know a lot about what's going on in the areas if there's no background seismicity or very low. So this is something I found extremely difficult because ideally we want this to be set up for in real time. But for in real time, we need information on the background seismicity or the stressing rates. Otherwise, we cannot forecast what might happen once you start injecting. So that's something we're working on right now, and also including operational management strategies. So we want to have a whole slide that basically says, okay, if you're expected to exceed a magnitude X in the next however many days, then you should do this to your injection, or you should stop it, or you should, you can continue. If you continue, you're likely to see this and that. So yeah, that's it.
Thank you. Early career questions first, sorry.
Either everyone's super happy or super confused.
Als allemaal gezegd is, we're still waiting for. Okay, let's do it in that order. Let's do them all, because
So, thank you very much. You said somehow near the beginning that you were using this constant stressing rate for the area. That was a hypothesis, but I'm more confused about what numbers do you how do you estimate that? Do you tune it on the catalogs, or do you?
You mean the values of the normal and shear stressing?
Yeah,
Oh.
Places, because we have no idea.
Well, exactly. So we just, for this specifically, we had no other option really but to use existing ones. So we used what they found in Oklahoma. I think Norbeck and Rubenstein used 10 to the minus something, 10 to the minus 4 and 10 to the minus 6. We are actually in the process of at least discussing a whole new project that could look into this further. But it's such a big thing because there's so many areas where we don't really have background seismicity, and we can find out that it's probably like a decade-long, yeah. So the truth is, unfortunately, so I did some work on just varying the stressing rates to see what happens, and that way we maybe got like an estimate of what we think is happening here, but we really have no way to constrain it.
Chris?
Really nice talk, thank you. Wondering if you've looked at time-dependent changes in anything, like as a function of injection, do you try to resolve changes in the local permeability, things like that? The way you would maybe in the geothermal field? Or?
So there is an option, I think there's an option in the physics-based models to do that. I have not looked at, like, on the statistical side. So it's very, I would say, rough at this stage. We've taken like the existing catalog and tried to just take chunks of the data to see if we can model the rest of it. And we have tried different things. We've tried time-dependent, time-independent. We've tried declustering, not declustering. Of course, some of those are not really feasible once we try to go to real time. So yeah, we're kind of trying lots of avenues to see what fits best, and then hope it will also fit well in a different data set.
Forge and collab to other geothermal sites?
Sorry, we have not applied it to Forge. It is applied to one geothermal site in California, I think, but I need to ask Kayla for sure. All of that is mostly like internal. We haven't really published or talked about it very much. So.
Jean-Philippe?
Yeah, a question regarding the level of clustering that you observed in Cato, because we looked at that site too. I was surprised to see that there was a lot of aftershocks. Is it also something that you found?
Yes. So I don't have a good image of the person working on like the CRS and the physics-based side, but he's got some really good plots of basically showing all the clusters and how close in time they are, and all of the aftershocks. So we definitely, all of that seems to happen towards the beginning of injection, like within the first year or so, year and a half. I just recently, like last week, tried to decluster the catalog that I've been using. We've kind of been on and off about whether we should or shouldn't decluster, and I think there's pros and cons to both options. Ultimately, that once we go to real time, we can't really discern what is foreshock, main shock, aftershock. But there is definitely clustering, and a lot of it at the beginning, of this. And that's where like my model, hopefully the ETOS one will be a little better, but this one specifically does a really poor job at estimating like what's actually going to happen. All it does a good job at really is estimating the temporal forecast at the end of injection. So.
Thank you again. We move on to the next speaker. But maybe we can stop 10:35. So like this, I will stand up.
I'll try. I have to do the best. Yeah, sure.
Okay, our next speaker, the last speaker before coffee, is Ioannis Stefanou on earthquake controllability and prevention. You give him some seconds to set up.
Yeah, sorry. Okay. All right. I don't know how to install this.
So, you have several options. You can put it over your ears, like this, or you put it like that.
All right. Okay.
You can choose.
All right, I'll put it like this. All right. Thank you very much for the invitation. We will talk about some new ideas that try to bring control theory into the problem of earthquakes and induced seismicity. So half of my presentation, more or less, will be devoted into presenting the basic ideas of control theory without getting into details. But first of all, I would like to start with a simple game. So I invite you to take your pen and try to stabilize it vertically. Do this experiment. So you try and you move your hand to stabilize it vertically. And for Chris, I have a special game. It is called the two-core game. That you try to do this, but with one finger like this.
No, listen, you have to do it though.
No, it's the other game now. So try to do this, and oh, no, without cheating. No, don't hold it. No cheating. And if you manage to do it, that I strongly doubt, then close your eyes. You'll see it's impossible practically. It's impossible. What I would like to stress here is we need feedback to hold it vertically in the best case scenario. It's like driving a car. We cannot drive a car even we are very good drivers without having our eyes open. At least I cannot. So let's try to analyze a bit more this very simple example that in theory we can measure perfectly. I can have the distribution of mass of this. I can measure the angle, the rotation, the angular velocity, everything. So we'll need some prerequisites. So just import from your mental Jupyter notebook, import curiosity and some basic knowledge of ODs, all right? And let's start from the, for modeling this problem. So we have a mass, okay, let's say that's concentrated here. We have a rod that is massless in this example, and we have a pin. So this mass can rotate around this point. We know perfectly L, we know perfectly M, and we denote with phi the angle of rotation. We have the gravity, and we will try to apply an input here, a moment, a torque, such that to stabilize this rod vertically. Still I can't. So now let's see what will happen if we do a very, of course this is an unstable system. It has two equilibria. One it is both are vertical, one is this one that we can prove that it's unstable, and the other one is this one that we can prove that it's stable. So let's start from the vertical position, do a very small perturbation. Yes, so this is the equations of motion of the system. You see it is a nonlinear system because it has the sinus of phi. And then I will rearrange the terms. and allow me to do, for the sake of this presentation, a linearization of the equation, which is not necessary, but it is very easy to follow the developments later on. And now I will solve this equation numerically or analytically if I wanted, with a zero input, with a zero torque. So we'll see here that I do a small perturbation, a very small angle of 0.1 rad, and I will give an initial velocity, and I will see that, of course, I will diverge from the zero solution. That means that the rod will turn and will start cycling because I don't have dissipation in the system. Just to show that the linearized system and the non-linear one, in the vicinity of the zero angle, they coincide. Okay, just to be a bit more convincing for those that would like to study directly the non-linear system. Now, there is a term in control theory that's called open loop. That means that I will try to find the time evolution of u of t in such a way to achieve a desired state. The desired state is to bring this mass and keep it steady at the zero, at phi equal to 0, okay, to have it like this. So, as I know perfectly the system, I do my calculations, you can follow different methods, and I can find the function, one of the functions that can bring back the mass and keep it steady at the vertical position for these two initial conditions. And indeed, if I do that, this is the solution of the equation that I will find. You see that here I have the exponential with a minus here. That means that eventually we'll come to 0, the angle phi. And if I integrate this, what I expect, I find that I start from a 0.1 phi, and then eventually I will go to 0. This is the open loop. But what will happen if I add a very tiny perturbation at the initial condition here? Tiny. 10 minus 4, 10 minus 5, 10 minus whatever you want. Well, in this case, I will solve again my equation, and I'll find the appearance of this exponential term with a small constant epsilon here, that after some time will dominate, and my system will start diverging. See here, at the beginning, I was following the good tendency. It was going towards 0, but after a point, pop, it diverged. Because of this tiny perturbation, I think this numerical simulation is with 10 minus 4 as a perturbation at phi. Now let's go a step further and do the same thing. We know, let's say somehow we know perfectly the initial conditions, but I do a very small perturbation at the mass. Very, very small. Again, I will see the appearance of this exponential term that is not compensated by the input that I input by solving the equation, and you see that after a point I will diverge again. So that's just an example to show that if I'm in an open loop, even if I know my system exactly, small perturbation cannot allow me to make it behave as I want. But maybe there is another solution. And this is the notion of closed loop, meaning I have feedback. Somehow I measure my system. I probe it and I measure it. And if I have feedback, maybe I can do something more. So this is the closed loop. This is in control theory, this usually is the system. It's called plant. In our case, will be the earthquakes. We'll talk about this later on. And it has some outputs that I will read. And I will need to design a controller, meaning a function. It can be an operator. It can be a computer program that will calculate, that will have as output the input to the plant. I'll show you an example just after that. And this is a closed loop. Well, in this, I can take also into account some perturbations. I can take into account the fact that I have many uncertainties in my system, and so on. So let's see an example. The same. Let's say that with some measures, with some sensors, I measure the rotation and the angular velocity of this rod. Okay, that means that somehow I measure phi and phi dot. Okay, and let's use as input now a function, a linear combination of these with some parameters alpha and beta. Okay, so I will inject this here. I will factorize the terms, and I have this OD now. Now this is the closed loop system. The characteristic polynomial of this is this equation here, and we know basic linear stability analysis, that if the polynomial, the characteristic polynomial has all the roots of the characteristic polynomials are strictly negative, then the whole system will be asymptotically stable. But you see here I have two parameters, the alpha and the beta. So maybe I can solve for the eigenvalues. Here they are, and maybe I can find a beta and an alpha such that both S to be negative. Well, in this example, this is the case. I will apply Vieta's formula. I will know that the product of these two eigenvalues is equal to this term here. And I know that the sum is equal to this term here. So if I choose an alpha such that this term to be positive, that means that both roots will have the same sign. And if their sum is negative, that means that both roots will be negative. So I will choose an alpha that has to be, by rearranging the terms here bigger than mgl, and a beta that is strictly positive. Notice that if I choose a sufficiently large alpha, I can compensate a large margin of uncertainties in the knowledge that I have about the physical system, which is its mass, the gravity, the acceleration of gravity, and its length. And let's see what it will give. I will choose an alpha that is equal to 8, and a beta is equal to 4. And indeed, you see, I start my system, and I go directly to 0. So, thanks to feedback, I can give the input to the system in such a way to achieve my control objective, which is to bring it to the vertical position. Now, okay, you will tell me that this is a very, very simple system. And I will tell you indeed, but still there are a lot of nice properties behind. But let's add some complexity. So there's a video here.
One property of chaotic systems is that no matter how hard I try to set this off in exactly the same way twice, minute differences between the way I release the pendulum each time mean that the motion ends up looking radically different. Let's rewind and try that again slowly. Because they were released from almost the same position, they start off moving quite similarly, but slowly at first they drift apart, and eventually the very small differences between how I release them are amplified, and the pendulum's motion looks erratic, completely unrelated to each other. This chaotic motion is actually impossible to predict precisely.
Well, to predict precisely, right? Which brings us to the notion of forecasting. But the fact that it's chaotic, the fact that I cannot have a predictive capability of the system, this does not mean that I cannot control it. And I will show you an example. Let's take the double pendulum here. And you see this card? So there's a controller that was designed behind that moves the base in such a way that will stabilize the system to different positions. These are different energy levels in the system. So we can play actually with the system. You see? I can control the potential energy that the system has inside it. I can make it dance. The system is chaotic, non-linear, difficult system. But not as difficult as the systems that we would like maybe to apply all this framework, which are earthquakes. Now, I don't have a lot of time to get into the math, so I will try to give some of the results that we got in the group. And yeah, this continues forever. I mean, we can do whatever we want. So let's talk about earthquake control. Well, if these systems were in the community of control theory at the beginning were difficult, if we was about to talk about earthquake control, this is another level of difficulty, at least in my opinion. Well, what would it mean in this case? In this case, would be our physical process of earthquakes. It can be one fault, it can be a network of faults, it can be a reservoir, it can be a very complicated system. It has some outputs. We measure things. We measure the seismicity, we can measure the subsidence, we can measure pressure, we can measure different things. So it has outputs, the system. It talks to us. So we try to read this, and then we will investigate if there is a controller here, if we can design a controller such that to adjust the inputs of the system, that in the cases that I will discuss, it is the fluid fluxes at some wells, in such a way to achieve the control objectives. It means to stabilize the system or make it move in a controllable way. The problem, though, it is that there are many difficulties. The systems that we are tackling are unstable. They are strongly non-linear. They are uncertain and unknown. We will never be able, well, maybe, I don't know, but in principle, it seems that it is unlikely that we'll know exactly the parameters of the system, the properties, and their distribution in space. The system is underactuated, meaning that we have less inputs than compared to its degrees of freedom. And another difficulty is that the system is continuous. In other words, it is described by a partial differential equation or by a set of partial differential equations rather than ODEs. All these are very important challenges for this branch of applied mathematics. It's called control theory, and we have to push the bounds and develop new controllers, if possible. Small parenthesis, all systems are not controllable. So we might prove that some systems are not controllable and we can do nothing. Okay? So, but we were lucky. In the case of a single idealized fault, we're lucky and we have proved that if the friction belongs into a sector, here, where x is the velocity, is the slip or the slip rate, that means if the friction is bounded, it's a certain degree of regularity, then we can, and if the friction has a lower bound that's positive, okay, this we expect it from thermodynamics, and if the diffusivity has a lower bound that is greater than 0, except, again, this will be guaranteed by thermodynamics, then we can design an output feedback stabilizing controller and we can achieve asymptotic tracking. Okay, this is a long phrase, which practically means that we can design the kind of cruise control as we have in our cars, but for faults. You know, in our cars, we set a speed and we say that we can speed with 30 maximum kilometers per hour. And the regulator behind the controller, independently of the uncertainty of the system, we don't know, for example, we don't know the steepness of the road, we don't know the pressure of the tires, the number of people that they are in the car, but it will regulate the power of the engine such that to succeed and keep this velocity constant. Well, we try to do something similar with a single fault. Now we have proved this mathematically, and we have designed the controller. And I won't get into the mathematics there; they're quite hectic. But I will show you some examples, some numerical simulations first. And we imagine a fault that has a length of 3 times 3 kilometers, I think. And somehow we measure the average slip over the whole fault. And we have 4 wells here that they are not on the surface, but in a distance from the fault, that cover, the front of the fusion will cover 1/4 of each fault at its time. Now let's play with this academic example. First of all, we won't do control, we'll do a simulation, we'll see that we'll have the instability, we will start somewhere close to the critical point of the system, and we'll see that after some point, we'll have the increase of slip. The different lines correspond different points over the fault surface. And if we see the slip rate, we have something of the order of 0.1 meter per second. And the slip, it is of the order of an average of 250 millimeters in 15 seconds. Okay? Now, this is a very exciting problem. And we saw many, many nice simulations. But what we're trying to do is something that is really boring. We try to slow down the system. Have the same slip or even more slip, but not in 15 seconds, but in 1 year in the simulation. And indeed, now we will activate the controller, and we will try to, we'll set as objective to drive the system on average to a slip that is of the order of 500 millimeters here. And the control objective is succeeded because the theory says so, actually. So, and the numerical analysis confirms. And you see that for this control objective, for this scenario, we have velocities that are of the order of 10 minus 7 meters per second. In other words, we managed to release all the seismic energy that was released in 15 seconds, but in 1 year. So the dynamic effects are prevented. Okay, and now let's see how the wells behaved. I mean, what were the pressure at the injection wells here and then on the fault. The blue lines corresponds to the pressure, the average pressure over the quarters of the fault area, while the black lines correspond to the pressures at the vicinity of the tips of the wells. And we see a small delay because we take into account diffusion phenomena. So we have a small delay that is inherently taken into account in the control design. Okay, numerical simulations are very good. Let's go to an experiment. So what we did is that we built a double sear apparatus. Here you see the piston that simulates the far field, the tectonic displacements. We have the elasticity of the surrounding rocks. It is more or less like the machine that you have in Italy. And we have a fault interface here. The blocks were printed by sand, which gives us a lot of flexibility of doing exotic things. And the difference of the system is that we have a pump here and a balloon that allows us to adjust the effective pressure relatively fast. So what we do is that we read the displacement of the middle block, and we adjust the pressure based on the controller or the regulator that we have designed. Now, this is the experiment in reality, and I'll show you a video just to convince you that we had instabilities, and then we'll try to compensate them, to activate the cruise control. So you see here the spring. We load it slowly. Now it's compressed, and as we expect, after a point, we have the first one, we have a second one, here a third one, and so on until we reach the bottom. And if we measure the velocity, we have velocities that are of the order of 0.35 meters per second, and a slip that's of the order of 7 millimeters with the design parameters of this experiment that we did. Now the scenario is to activate the cruise control and avoid all these instabilities, pass through all these unstable zones in a controlled way. So what we'll do is that we'll try here to make the middle block to follow this sigmoid curve, meaning to have more or less the same slip, but not in 50 milliseconds, that was in the experiment before, but in 1 hour. So again, a very interesting problem that becomes very boring. So actually it does it, the regulator. You see how closely it follows the reference slip. These jumps here is because of our discrete sampling in time. And this is the velocity that on average follows the reference. And we have these peaks because of the discrete sampling and also noise that exists in our measurements and also in the specimens, uncertainties. But they are very small. They are talking about some millimeters per minute, these velocities. So it does it, and this is the input of the system. This is how it regulates the effective pressure. So if we were injecting fluid, this would be the pressure over the fault interfaces, the lab fault interfaces. And we see that at the beginning, the system was in the vicinity of its critical point, but it was in a stable point. So it starts injecting, increasing the fluid pressure, decreasing the effective stress, and then somehow it understood that the system had a tendency to go unstable and started reducing, and then it had this very strange behavior that guided the system from 0 to 7.5 millimeters. It passed through all the instability zones, thanks to the controller. Now, repeatability, we did this test several times. All of the times we follow very well the reference, but the input signal is very different. So it is repeatable in the sense that the control objectives are achieved, but the input is totally different. That means that I cannot take one of these curves, put it in another experiment and an open loop approach, and that it will work. It won't. So you see, there are big differences, and this is because of the uncertainty of the system. I forgot to tell you actually that the design controller is agnostic to the exact parameters of the system behind, meaning that we don't know the exact frictional rheology. We don't know the stiffness. We don't know the diffusivity in the numerical simulations. We have just very large estimates. Okay, this is one example. I have other ones, but we don't have a lot of time. I have how many minutes, maybe?
About 5.
5, okay, good. Okay, so I want to squeeze some neuroanalysis, very recent actually, that have to do with the example that Jean-Philippe presented, the Groningen. Thankfully, I won't need to spend a lot of time on that. This is geometry. We have 29 wells, and this was the production of gas from 1965. Groningen field gave more or less 10% of the gas needs of Europe during these years, and it was closed in 2024 because of induced seismicity. Now we have designed a special controller behind that's different from the one for a single fault, and I will try to show you the principles behind this design and how it performed. The target now is not to avoid only induced seismicity, but on the same time to maximize production. So we have two antagonistic processes here. Now, first of all, we designed the controller. The controller was designed to be agnostic to the specific parameters of the system, but in order to demonstrate it to you, I will try first of all to have a plausible system. Now, what we have done is that we're based to the works from the group of Jean-Philippe, and we try to extract as much information as possible, and then simplify it. Because we don't want to do forecasting, we don't want to have a detailed model. We just want to have a model that more or less follows well the experimental data for the whole duration of the extraction of Groningen, and then apply the controller. Now, that said, I would like also to thank Matteo for his help to deciphering the data behind, Matteo Acosta. And our simplified model was based on a depth average of the 3D diffusion equation that is coupled with the nonlinear OD for the seismicity rate that we saw in the two last presentations. Now, if we couple these two systems, we have three unknown fields. We have one data set, so the system is overdetermined. So we found the local minimum based on a gradient optimization technique in order to determine the parameters of the seismicity rate model and of the diffusion equation. And if we do that, we see that we more or less follow well the cumulative events in the Groningen site. Okay, it's a good fitting that we did, just to have a simple model, and then we can compare based on this fitting the spatial distribution of the seismic events. This is what the real events give, and the colors are more or less the same. Actually, it's made two because it is optimized on this data. Now, let's talk about the robust control. The objectives are to force averages over pressure over residential regions to follow desired references. So we went on the map and we saw on Google Earth some cities here, and we said, okay, there we would like the average pressure to remain more or less constant because we don't want to accentuate subsidence. And then the rest region in orange would like the seismicity rate to be equal to 1. In our scenario, 1 is 1 event per year. Before we're having around on average 20 events per year. We could put 1 event per 10 years, but this is a scenario. And we'd like to assure net gas extraction, as in the Groningen. And in this example that I will show you, in the same time we will inject CO2 inside in order to have a zero carbon impact. Now, the challenge is that the system is continuum. It's of infinite dimensionality. We have nonlinearities, and we don't have actually access to its exact parameters. So even we fit the system, we don't use this information for the control. And the solution was to design an output feedback, multi-input, multi-output, robust controller using minimum information. I'll show you the results. Here you see the average pressures over the 5 regions that we chose, that we set a reference, we set them to go to 14.37 megapascal, and the controller achieves the control objective. So over these regions, we don't change a lot of the pressure. And most importantly, the seismicity rate follows the reference, which is the gray line here. So we don't increase the seismicity more than one event per year. That was the control objective. If you want to put 0.5, 0.25, you're free to do it. It will work again. Now let's see the fluxes at the wells. It is this very strange thing that I cannot really understand and see what's happening. It is quite messy. This is what is calculated automatically in real time by the controller. This is the demand. This is the extraction that was made at the Groningen. We follow it exactly. When I'm saying exactly, with a precision of 10 minus numerical precision. And this is the injection of the CO2 that we applied the factor in order to compensate the CO2 impact of the gas that we extract. And in our words, we managed to extract the same amount of gas. We managed to, with this controller, we managed to inject CO2 and have a zero impact and not increasing the seismicity rate. So maybe if we had this theory some years ago, maybe Groningen would be open. Who knows? So some key points, and I would like to close with that. We've proven that earthquakes from a single fault is an instability that can be, in theory, controlled by fluid injections. Control theory is a large framework that allows us to provide rigorous proofs, and I would like to insist on that because we have mathematical proofs that will tell us about the controllability, stabilizability, and observability of the system. These are notions that we need a lot of time to explain, but they are important because they show us what we can and what we cannot do in a real case scenario. And I see a very important potential for enabling key technologies to reduce CO2 emissions. Of course, control theory is in the heart. And in the abstract, I would like to talk, I promised to talk about reinforcement learning, but there's no time, so maybe a next time. And with that, I would like to thank all collaborators, Yorgos, Diego, with which we write huge whiteboards, Philip, Frank, Matteo for his help, and of course Jean-Philippe for the numerous discussions that we have done so far. And thank you.
Thank you. Questions?
I have two questions. Starting for the first question.
I have more.
Okay. So it's like we may have multiple measurements, like in the field. It's like we have sleep or slip rate deformation related, or we have seismicity related. So is there a preference when you want to control this, when you choose these parameters?
This becomes a techno-economical question now. What we will also try to answer in the next year is what would be the optimal sensor placement and number, but as well the optimal actuators placement, meaning how many wells and where you should put them. So I don't have an answer to your question right now, but if we have a cost function, then we can start developing optimal scenarios for optimizing our interventions.
And the second question is that because you show the numerical simulations and also you show the experiment, so basically it's already a well-defined system, if I understand well. But in the field, for example, we may not in that case.
Yes.
So how robust is your theory, like your strategy, when you're trying to apply this kind of theory to application?
Yes, yes.
Or
Well,
for example, if you have kind of like a black box,
yes.
How much information do you need to?
So what we try to do is to provide proofs that that need minimal information about the system, meaning that we don't need to know its exact parameters, but indeed we have some basic physics inside it. So, for instance, if you take the controller that is used to land the Starship of SpaceX company, it won't work in this case and vice versa. But we try to take a maximum amount of uncertainties into account for designing the controllers. So.
And another, well, let's rephrase it another way. Whether mechanical simulator is necessary behind, or it's like.
Why mechanical simulator?
Yeah, like a mechanical simulator. How do you simulate the fault, sleep, and?
We don't need the exact information about the rheology of the fault, the friction, all this stuff. But this does not mean that if we don't have this information, we won't use it. If somebody gives this information, then our controller will be more optimum for the specific case. But we don't need it.
Yeah, question?
reasons why it may not work, or not a few why it may work. I think one important question is, for one fault, I understand it may not work, but when you have fault interaction, you may trigger a slow sleep, but problem is many controllers working on each fault of the system, right?
Well, this is a scenario that we will run. If you have many faults, practically you change the stiffness of your system. Mathematically speaking, you have this, the matrices that change, the connectivity that changes. So in theory, I think that should work, but we have to check it to answer to your question. So, but we need to have enough inputs for the outputs that we want to control. With one well, you cannot control 2 faults, for instance. So you need more. No. Yeah. Yes, and you need to assure us some controllability conditions. For instance, you cannot, by injecting in Cargèse, you cannot control the sleep of the San Andreas fault. This is.
One last question.
Does the feedback, at least in the lab, has some universalities? The feedback that you get from the lab to control?
Universalities in the sense?
Some pattern that look like it makes sense in an analytical form.
I don't know if I understand well the question, but the experiment.
Is it a simple fitting, like
What?
exponential?
No. It's totally no. There's no. We cannot. An open loop approach won't work, even if we fit it very well with analytical functions.
Let's have coffee. Thank you.
Thank you. Voilà. Huh? Thank you. Thank you.
Your answer to Pierre.
Yes.
In the Groningen case,
Yes.
there's thousands of faults, and you're controlling it.
It is based on the seismicity rate model.
The pressure that is controlled. The pressure in the reservoir. It's not the flow.
It is the flux that changes the pressure that changes the seismicity rate.
Yes.
Pressing questions and perspectives. Thank you.
All right, thank you very much for coming back. So we have Natalia Berrios-Rivera, who's going to talk about models of injection-induced seismic slip. So the floor is yours.
Okay, thank you. Yeah, I'm going to be presenting my work on modeling injection-induced seismic slip with permeability enhancement and rate and state friction. So injection-induced seismicity can occur as individual larger events or as swarms of microseismicity, and I'm going to be focusing on the swarms. So in swarm seismicity, swarms are often characterized by a diffusively expanding migration front, which is like in this figure here. And there are two possible explanations, or there are many possible explanations for this diffusive space-time behavior, but two that are commonly referred to are fluid pressure diffusion and elastic stress transfer from fluid-driven aseismic slip. But there are some potential issues between these two mechanisms and how they match up with observations. So if we assume that seismicity is just driven by fluid pressure diffusion, and we try to calculate the hydraulic diffusivity of the fault zone using the observed seismicity front, then this can result in values of hydraulic diffusivity that are orders of magnitude larger than what's observed in the field or in the lab. On the other hand, with elastic stress transfer from fluid-driven aseismic slip, this addresses the issue of needing the high hydraulic diffusivity because it has a similar diffusive behavior, but that expands faster, but it suggests that most of the slip is, or that there's a significant amount of aseismic slip, and in some cases of swarm seismicity, there's not a lot of direct evidence of aseismic slip. And this can be because aseismic slip is difficult to resolve at the surface, or it could be because there's just not a lot of aseismic slip happening. So we're going to try to sort of reconcile these models and the differences between them and the observations through our work. So we're doing 2D earthquake sequence simulations of constant fluid pressure injection into the end of a dormant fault. So the fault has velocity weakening, rate and state friction, and permeability enhancement that is described by this linear equation. And because we're assuming it's a dormant fault, we have this high permeability contrast between the interior of the fault and or the part of the fault that has slipped versus the outside of the region that has slipped, which has a lower permeability. So we ran a parameter space study where we varied the state evolution distance and the pre-injection stress state of the fault. The pre-injection stress state is quantified by this stress injection parameter, which is characterizing the pre-stress state of the fault relative to the strength change from the fluid pressure injection. And these are some of the results from the simulations. So I'm only going to be showing results from 2 of the simulations, one where the fault was more critically stressed prior to injection or closer to failure, and one where the fault was more understressed or further from failure prior to injection. And these are space-time plots of slip velocity. And we can see that in both cases, there are some larger events that tend to rupture back to the injector and some smaller events in between the larger events. And then in all cases, most of the events are nucleating near the slip front. I'll also note that there's a lack of complexity in these models, and that's probably because this is a planar fault model with constant friction and constant stress parameters. And so we attempt to address this lack of complexity in this seismicity distribution with some non-planar fault models that I'll show later on. But for now, just looking at the planar fault model results, we see that most of the slip is seismic in all of our simulations. And we also see that although all the slip is seismic, aseismic slip still plays an important role in the process of permeability enhancement and weakening the fault. So the fault will slip aseismically first, which increases permeability, which allows fluid to flow into the fault, weakening the fault, and then basically preparing it to slip seismically. And so we want to compare our simulations to an analytical solution for a fluid-driven crack. This is a crack model for a fluid-driven aseismic crack. And these are some of the assumptions made. It's based off of a lot of previous work that's been done modeling this aseismic crack propagation. But the important thing to note is that this is a crack model for fluid-driven aseismic slip, and we're going to be comparing it to our simulations where most of the slip is seismic, as I showed in the previous slide. So in doing that, this equation comes from the aseismic crack model. It basically is telling you where the position of the aseismic slip front is. And we fit this equation to the slip front in our simulations, and that's shown in red. Here I'm plotting it over the space-time plot for pressure. And we can see that the solution from the aseismic crack model coincides with the slip front from our simulations. And the slip front is expanding diffusively, but with this sort of behavior. So it's expanding faster than it would if it was just, than what's expected if we were just considering fluid pressure diffusion. And so these again are the 2 cases that I was showing earlier, and we see the same fit for all the simulations that we ran. And in fitting this equation to the slip front, we can get this parameter lambda, and lambda quantifies the crack tip speed relative to the hydraulic diffusion length, and we use that to compare the simulations and the analytical solution a little more. So here, that's what I'm doing. So T is again the stress injection parameter. So as T decreases, the fault is closer to failure. And then on the x-axis is this parameter lambda. And so as lambda increases, it indicates that the crack is propagating faster. And we see that the analytical solution and the simulations have the same lambda T relationship. So the analytical solution is in blue and the simulations are in purple. And they match very well. And so again, this is a analytical solution for aseismic slip and simulations that show mostly seismic slip. So it's not necessarily, we didn't necessarily expect them to match up. But I'm also showing these green triangles which are for non-planar fault simulations. And this is the lambda t relationship from the two reference simulation cases that I was showing, but for a non-planar fault. And the offset to the left is due to the rupture propagating slower in the non-planar fault simulations. So this is the profile for the rough or non-planar fault simulations. So we are adding complexity by adding heterogeneity to the normal stress distribution, and that results in these simulations that again show a diffusively expanding slip front that we're able to fit the aseismic crack model solution to, and we see the same diffusive behavior and that the solution coincides with the slip front. And so what we saw in the planar fault simulations isn't just unique to those simulations. We also see it in the non-planar fault simulations. And then looking at the space-time plots for slip rate, we can see that there's more complexity in these simulations, which is what we were lacking in the planar fault simulations. And so you can see that not all the events are nucleating at the slip front. Some of them are nucleating inside the leading edge of slip, and some events tend to propagate both back towards the injector and away from the injector, which we weren't seeing in the planar fault simulations. And then just to kind of get a sense or a better sense of how the seismicity distribution varies temporally, we can look at this plot. I'm plotting potency, which is basically a measure of the size of the events, on this plot we on the x-axis we have time, and then on the y-axis we have the fault length. And you can see that there's some clusters of microseismicity here and here and here, and that's sort of like swarm-like. This is what we're calling our swarms. And there's some larger events in between. And we're not able to match this to data yet because these are 2D simulations, but it is showing some behavior that's similar to what we would expect from an earthquake swarm. And so I hope that I've shown you that seismicity can be driven by fluid pressure diffusion and elastic stress transfer from seismic slip with minimal aseismic slip, and that we can use the analytical solution from an aseismic crack model to describe the behavior of the seismic slip in a fluid-driven swarm. And although most of the slip that we observe is seismic, aseismic slip is still playing an important role in the process of permeability enhancement and how that weakens the fault. And then lastly, the non-planar fault simulations show more complexity that matches some of the observed or the expected behavior of earthquake swarms. So, thank you.
Thank you very much. Time for questions from PhDs and postdocs first.
Are those backwards propagating slip fronts similar in physics as the back propagating tremor fronts that we see in slow slip and tremor zones? Just because they're also involving fluids and have that same kind of characteristic.
Yeah, that's a good question. I'm not too sure about that. I haven't looked into that, but that'd be a good thing to look at.
What does the permeability because? Like, I didn't have time to look at the equation, like the permeability enhancement.
Like the equation for permeability enhancement?
Yeah, so it depends on sleep, right? Is it kind of Seagal on rise?
No, this is just like a very simple linear equation for permeability enhancement. So there's observations that permeability increases as the fault slips, and we're just trying to add that into the model in the simplest way, which is just as the fault slips, it goes towards this maximum permeability value.
Can it recover?
No, so once the fault slips, yeah, there's no healing, basically. There's no healing term. Yeah, so only permeability enhancement.
Yeah, thanks, Nessa. I had a similar question about permeability enhancement because you only use it in the aseismic slip model, right? You don't use it in your first model?
No, it's in the simulations, and then it's not in the in the crack model,
Which is not in this one.
no, it's just we say that the outside of the crack is impermeable and the inside is permeable. So yeah, as I guess there is permeability enhancement, right? As the as the crack slips, like this region is permeable, the interior is permeable.
Yeah, because that makes sense that would increase permeability.
Any other question? No? Thank you very much.
Would you like to put it over your ears or around your neck?
I know.
Around the neck? Okay. I found my job for this
Yeah.
conference.
Thank you.
Thank you, Alice.
Thank you.
So we're going to make a job, and we're going to have to look at dust data. You ready? Okay. Well, I have to learn how to turn on the computer. Yes.
Sorry.
Wonderful.
Thank you.
Floor is yours.
This should be the first presentation, actually.
I don't think the point here is going to work.
Huh?
I don't think the thing to pass the slides is working.
Okay.
I think you might want to do it with the, yeah.
So hello everyone. Since my talk is maybe not that related to hazards, so I want to make it more related. So I will first talk about how what I need to do if I cannot open the door, because I have a lot of experience about this. So first you may call your roommate or call Anthony. Or you can just jump. So otherwise, I think I will ask Zoom link to present. Okay, so I'm a postdoctor from Xie and working with Jean-Paul and Pierrot, and other collaborators are from also Xie. And today, I'm very glad to share our recent work about the back projection and its application to the dust data in Chile. So you may already know, at least from Tuesday's presentation and the tutorial, that back projection is a method to check the rupture front of the large earthquake by making use of the high-frequency signals recorded by a dense array, so that you have relatively high resolution due to this high frequency. When I say high resolution, it's not as high as the aftershocks. It's about maybe only 7 kilometers or 10 kilometers, but still it's among the most highest resolution method to image the co-seismic rupture in nature. And another advantage or motivation to apply back projection is that it has high stability, because it doesn't require the information about the geometry or rupture speed. Instead, it can provide the rupture region so that you can use this information for further considering the other inversion-based method. So you can use it to maybe build a warning system, so also related to natural hazard now. So usually people use tiny seismic waves for back projection, as what you learned in the tutorial, because the phase will be much more simpler. And also you can catch a lot of large earthquakes using existing arrays. In most of the cases for the large earthquakes, you will probably have over 2 tiny seismic arrays available.
But to increase the resolution from maybe 10 kilometers to higher, so that we can explain or be more confident about details about a large earthquake or to image a smaller earthquake, we can either increase the frequency band using larger arrays or using closer arrays. So that's the motivation for my projects, which is about to use local seismometers arrays to image large earthquakes. But usually we don't have this available because we don't know when is the next earthquake, so that we can install very dense arrays around that region. But we still have strong motivation, also because it's closer to the source, so it can be used for early warning. So the dust technique provides us new opportunities. This article shows us the strength of the dust data for back projection because it has a high resolution, which is about 2 kilometers, so that it can resolve the sub-events of a magnitude 6 earthquake. So for me, the dust data is perfect for applying back projection because it has a very long length, so that theoretically you can cover a lot of seismogenic zone, and the density of the sensors are as high as 4 meters, and also because they are very long, theoretically they have very high resolution. But there is also some challenges. For example, these ocean bottom cables are over the sedimentary layers, so they have very strong scattering, and this linear geometry also makes it challenging to locate the sources. And besides, the saturation problem currently are not covered in the current research, and it's maybe challenging for local large earthquakes. So Jean-Philippe has accumulated a lot of data and experience about processing of ocean bottom cable data. And our data comes from this group, a ERC project led by Diane. And they have engineer Mahi and two postdoctor Alice and Martin and PhD student Kaha. And they first use machine learning to automatically detect arrivals and build a catalog. And then they will have monitoring about the seismic velocity change. And also they are developing an earthquake early warning system. And Pablo and I are collaborating with them to test the performance of back projection to this data set. And they insert interrogator and get and we first test the performance on this segment, which has a length about 150 kilometers. And this is a recording of the original stream rate data after filter to 1 to 4 hertz. And our first processing step is to integrate from the stream rate to the velocity so that we can improve the coherence between the waveform. And the second step is to correct for the sedimentary layers, so we have relatively higher accuracy for the travel time compared to these theoretical S arrivals. So these are both of these two techniques are recently published in Jean-Philippe. And after this pre-processing, we first divide the whole cable into several segments, so that within each segment, the waveform coherence is relatively high, so we can measure the slope more accurately. And this is the result of the back projection using synthetic waveforms, which is shown by this red line, and the recorded data, which is shown by these black lines. So using this method, we can reach a resolution, which is about 4 kilometers. And how about other locations? We do a systematic synthetic test to test the resolution distribution around the cable. And we also check the stability of the locating to the area of the velocity structure if we assuming we are using an inaccurate 1D velocity model. And we show that within this region, we have relatively higher resolution and higher accuracy. method to more recorded point sources and show that consistently we can have relatively high resolution within this region. And outside this region, due to a lack of focus, the result is much more scattering. And the real strength of back projection is to apply to large earthquake. So we start from a synthetic test using this magenta stars, which is used as imperial congruence function. And the result shows that we can resolve the rupture speed and the location very accurately, assuming that we can remove all these velocity structure errors. So here we manually correct for these errors from the structure, which is maybe not possible for the real case. So in the real case, we needed to use either deconvolution, cross correlation, or velocity calibration to remove these errors. So that's an ongoing project. So previously we showed the performance using this segment, and now we have to add more. So in total we have about 450 kilometers long cable available so that we can cover larger region. For example, this is a magnitude 6 earthquake, which has clear P and S phases, including the aftershocks, and also the seismometers on land can be used to relocate the earthquake, the aftershocks, and then calibrate the velocity. Another ongoing project is using active source. So here is the geometry cable, and this is a distribution of 200 active source. Using this data set, we can benchmark and improve our method further. For example, we can try different beamforming techniques, or we can apply different methods about velocity calibration, and using, for example, different weighting for sensors to improve the accuracy and resolution further. And this is a collaborating project with 2 scientists from Peking University in China. To conclude, we tried to use back projection to dust data and show that we can find a high resolution, high stability region for a given geometry. And then we found that we have a resolution about 4 kilometers using a 1D velocity model. And our method works well for synthetic and large earthquakes, assuming the velocity structure is accurate enough. And ongoing works includes using active sources to improve the method further, and then apply it to recording the moderate earthquakes. So now this hat is like a synthetic test result, and this is what we can get if we didn't, or we apply our current method directly to the recorded data. And our goal is to at least catch a cat like this in the future. The last slide is about another project, maybe related to hazard using dust. So this project is about to use the cable as a pressure sensors to measure the pressure changes caused by the tsunami waves. So assuming you have a cable over the change and reach the coast, then this is the water elevation you may extract from the noisy data. And this is the synthetic waveforms from the Tohoku earthquake. So the challenge is it has very low signal-to-noise ratio, so we have to use a new type of interrogator which has relatively high signal-to-noise ratio at low frequency. And we need to filter the data, maybe using machine learning to extract this data and make it more solid. So that's pretty much what I want to show today. Thank you for your question and listening.
Thank you very much. Is there any question in the audience?
I think in this talk, dust is usually have an issue in the coupling with the ground and fiber optic fiber, and maybe some of the channel has a lurch or noise or there's no signal. And what kind of effort do you apply for denoising of those stuff or the
you are seeing coupling or and smoothing.
Essentially, do you apply some denoising process, denoising processing or not?
So here we are using an integration method that assuming you can have different coupling states. So you can see that in some places the color is darker like this one. So in this case, it will affect your integration. But this technique doesn't is a local integrator, so you can it's using a smoothing window to remove these accumulated errors, so that it doesn't require the perfect coupling. But still, it can improve the performance.
Thank you for great talk. And yeah, it's very useful to resolve small-scale earthquake source process, maybe. But my interest is there any limitation in your method?
I think the limitation, first for back projection, is one challenge is very difficult to integrate, to interpret the results because we don't know what they are related to the, for example, final fault inversion result. What causes high frequency radiation? So we need to combine different methods and different data sets to have a more complete understanding of what's happening.
So I want to ask how accurate you know your locations of your fibers. Have you also considered elevation changes at the ocean bottom?
So you are asking the accuracy about
Like
what?
you draw here the map of the fiber of the dust, but do you know exactly where they are at the ocean bottom? Or
Yes, that's a very good question. Yes, for the ocean bottom cable, one problem is that we don't know the geometry of the cable. So currently we didn't consider this, but potentially it can contribute and increase the accuracy because currently I think at least I know some projects are developing some inversion method to invert for the location of the geometry. It may be very different as the when people design.
Any other questions? No? Well, thank you. So, Sebastian, where's Andrew? Where's the boss? What do we do, boss? What do you think?
We have a bit of time to discuss, if we want. We can start working on the groups for this afternoon.
Is it possible to have the keynote now?
No,
because some people will miss it.
Okay, yeah, okay. Michael, you're...
Okay, you change your mind. Do you mind?
We have time.
We have 1 hour.
We have 1 hour.
Okay.
I thought it would be too short, but...
I think it's fine. I have you.
System here.
Huh?
It's a dynamic system.
It's a dynamic system.
Oh, I need to get one.
Yeah, sure. I have to set up.
So this is
So our last
this is not
speaker,
working, right?
No, I just use my
last
laptop.
speaker of the week actually is Michael Blanpied.
Just use PC.
Powered
Let's see if this
interpretation forecasts and risk mitigation strategies. We'll see if the forecast of the title still stands. Because these titles seems to be changing these days. So we'll see.
Let's see if this
Looks good.
is showing.
Yeah,
Perfect.
Oh,
perfect.
amazing.
Out of the box. And then it's easiest to put it in your ears. Yes, just or like this also fine.
Like that? Okay. And this in the pocket.
And then you could use this if you want.
Wonderful. Okay, a dynamically changing schedule here. Thank you very much to the organizers for inviting me to come to the meeting and giving me the opportunity to speak to you. Some of you at this meeting know me from the world of rock mechanics, which was a much earlier part of my career. I did my PhD and some of my early work at USGS on experimental rock mechanics, looking at frictional sliding, the sort of work we heard from Chris Marone and others. But over the course of my career, I shifted fields a few times. In the late 90s, I got into probabilistic seismic hazard analysis, looking at a source model for the San Francisco Bay Area, which put me in touch with the people who do this kind of work, including engineers who are interested in the results of PSHA. And then I've moved since then into a program management position at USGS, where I've been for about the second half of my career. And that has, where in the USGS Earthquake Hazard Program, I oversee our program's work in earthquake hazard assessment and research. And that's put me in touch with a broad range of research at a very shallow level, as opposed to the deep level that I had previously in rock mechanics. But it's also put me in touch with a lot of stakeholders and users of our information from our program. The USGS is a mission-driven agency. Our program is funded by the US government in order to contribute toward earthquake risk reduction in the United States. And so the research and monitoring we do is focused on actionable research. We call it applied research as opposed to basic research, for example. With the idea that research results can be put into use in models and products that will inform users and help to inform risk reduction decisions that can be made by individuals, communities, governments, businesses, and so forth, to make eventually the nation safer, so that we can anticipate earthquakes in order to be better prepared for them, be able to respond to them quickly and efficiently. And we don't have a lot of focus right now on controlling earthquakes, but as we heard earlier today, it's an intriguing idea. That's not our focus, but so what I want to talk to you about today is some of these topics that come a little outside of the scientific topics that we've been hearing throughout the meeting, but get into more sort of how we put science into action. I have to say, over the course of the last 4.5 days of hearing presentations, it's been really exciting. There is a lot of fabulous work going on across the whole spectrum of things that we've been hearing at the meeting. And in pretty much every case, I can draw a line in my mind between some scientific topic that's being explored and its use in something that will reduce risk in some way. And I will encourage you to be thinking, as you do your work, I'll be encouraging you to think about how to draw those lines yourself, whether you actually follow that line or just are aware of it in motivating your work. So let's see if we can actually use something to advance here. No? Okay. Okay, a little slow. So we're all motivated in different ways and different reasons to do the science that we do. Some of us are motivated by trying to understand the tectonics of the Earth. Maybe motivated because you have a love of rocks and being outside. You may be motivated because it's really great to work in a laboratory and do experiments. You may love to generate large models, simulations. And this is also one from the CyberShake model that was developed in California. It may be that you love going to meetings and giving talks or sitting in the audience for talks. It may be that that you love this sort of mathematics. Thank you, Sylvain. Or it may just be that you love beer, and so you love ageology. So, but there's other motivations for our work as well, and I think all of us who work in earthquake studies or in any kind of hazard field are aware that the underlying an underlying motivation for our work is really this sort of thing. It's that earthquakes cause real damage and real harm to real people and real communities around the world, and we would like to see this reduced. And so the work that we do is ultimately driven by this. Some of us are driven to attack this directly and some indirectly, but everything you do attacks this problem in one way or another. And as I said, you can draw lines to get from one to the next. So how we go about reducing that hazard is by, important way is by providing forecasts. People need to know that earthquakes are coming in one sense or another. If we have, and we can just look at a timeline, for example, here's an earthquake that's coming, centuries, decades, years, weeks, days, hours, or seconds from now. What can we do to provide information to people so that they can anticipate this earthquake and be better prepared for it and reduce the losses that they may encounter from it? We can provide long-term forecasts, decades away, saying that this is a hazardous area. What can we do to prepare for that? Intermediate-term forecast over years, perhaps months. Short-term forecasts, we've heard a lot about that today. Jean-Philippe talked about some of those this morning. And we do have some operationally deployed tools that we are all familiar with that work in various aspects of this timeline. One is probabilistic seismic hazard analysis. I'll talk a bit about that. This is what underlies building codes and other long-term risk mitigation decisions and actions that communities and countries take. Another is operational earthquake forecasting. This is a general term to describe operationally deployed, short-term, time-dependent forecasts that say something about an increased or decreased likelihood of earthquakes in the intermediate or short term. We also have what we conveniently call earthquake early warning. Some of it call last possible warning, but that operates on the timescales of seconds. We do have operationally right now a kind of a gap in this months to decades time period in which there's a lot of work going on, a lot of experimental exploration, but we haven't deployed as governments, as official agencies and so forth, forecasts that operate in this realm to a very great degree. So the current status is we've deployed some operational tools. These tools are useful in a wide range of mitigation strategies, but they do have limited accuracy and precision. I'll show you that they're based on some pretty simple concepts, pretty simple observations and science, and there's a tremendous opportunity to put our science to work in improving them. So we'll talk about three different things here. Probabilistic seismic hazard analysis. This provides a long-term forecast of the distribution of future earthquake ground shaking. We know that there is a great deal of uncertainty about the earthquakes that may strike over the course of, say, the lifetime of a building. PSHA, because it's probabilistic, tries to take into account all those sources of uncertainty in a quantitative way in order to provide a probabilistic estimate of ground shaking that will be impacted at a site. And this can support a wide range of things in structural design and so forth. Operational forecasting is it's authoritative forecast at a shorter time scale. These are based on clustering statistics typically that are very well understood, that at the time to take into account the uncertainty we have in the location, magnitude, and rate of future earthquakes. And this can drive a large range of short-term mitigation decisions, response, readiness for recovery, and so forth. And then earthquake early warning is an entirely different time scale and class of models. This is detecting an earthquake that is already underway, characterizing it sufficiently so that you can send information ahead of the seismic waves in order to allow very rapid decisions, typically automated decisions by systems or alarms provided to people so that you can take a fast action, typically on the order of seconds, before the seismic waves arrive. I won't be talking any further about that. We had a little bit of discussion about that earlier in the meeting. And then we have, as I said, we have this gap here where we don't have so many operationally deployed systems, but there is a great deal of research on what might be done. So in the United States, I'll be showing examples from the United States just because that's where I work, but most of what I say holds true in most of the world. This is the National Seismic Hazard Model for the US, and it's updated regularly by the USGS. It estimates the likelihood of strong shaking from earthquakes, of course, hot colors to cold, and it's a time-independent model, so this is sort of the static view of the distribution of hazard across the country, and it updated periodically. We update it every 6 years, and I'll show you why in a minute, to incorporate what we say best available science. What's best known right now about earthquake occurrence, ground motions, and methods for calculating hazard. So, and of course our history is that it actually does pretty well. Most of the earthquakes that have occurred in the last decades in the US have fallen in the hot colored areas. Not a big surprise. And so we have a fair amount of confidence for this. And also if you dive into what are the expected ground motions, it actually does pretty well overall in anticipating ground motions. The annual losses in the US that's calculated from this model is time average at $14 billion a year. So it's a significant amount of loss. Of course, that's extremely aperiodic. Northridge earthquake, 50 billion, many years, almost none, so forth. The way we construct the model, and I'll talk a little bit more about this in the next few slides, is really combining everything we know about the Earth that we think we know well. We have good recordings of seismicity. We have good information about quaternary faults, especially those that have been active recently. We have geodetic information that in parts of the country, especially the West, is very well recorded. And then we have good information and a lot of study on the relationship between the occurrence of an earthquake and the ground motions that occur in the surrounding countryside. So once we have a hazard model, I'm going to go back to PSHA in a minute, but once we have a hazard model, then what? So as I said, the USGS provides this hazard model. It's an estimate of the shaking over time periods with various kinds of intensity measures that one can inquire about. So we put out this report. Then what happens? Well, there's a whole series of steps that leads to the actual risk reduction. The first is the National Earthquake Hazard Reduction Program, which is several US agencies put together, takes this ground shaking and turns it into what was called design maps. This is estimates of the amount of shaking that will impact buildings, with decisions made about what is the level of safety that we should expect from our buildings. Typical building lifetime is about 50 years. One has to make then a decision, not a piece of science, but an actual decision about how much safety do we want. Typically, we say the absolute, limit is we don't want a building to fall down. Nobody should die. The building may encounter an earthquake and be completely unusable, and you throw it away and you start again, but nobody's died. And so there's a sort of a minimum collapse probability that is imposed in the engineering decisions that go on in this step. This then is passed to the American Society of Civil Engineers, which puts it together with all the other kinds of engineering considerations that go into buildings, wind, so forth and so on. That then is adopted into the international building codes for new and repaired structures and so forth. And then the international building codes, which incorporate everything about buildings, electrical system, fire resistance, and everything else, that's then offered to governments, local and state governments, for their adoption. And so, for example, California has a residential code that adopts the international building codes, and California makes the choice to do that in full. but they don't have to make that choice. They could make a different choice. So just to look at how this is put together, we have earth science over here. We have a set of engineering decisions that are made here. And then we have a policy decision, a political decisions made here. And governments take into account all sorts of information that go way outside the realm of earth science, way outside the realm of engineering, in deciding about costs, about convenience, about tolerance for change in the codes and so forth and so on in making that decision. So let's go back and talk about how PSHA actually works. Goes back to a very simple concept, which is the hazard curve. And what the hazard curve is, and you'll see some of these, so I'm going to just explain what it is. So this is the annual rate that some kind of shaking measure is exceeded. Is it yearly, every 10 years, 100 years, 1,000 years, 10,000 years? And the ground motion intensity. And this might be peak ground acceleration, it might be spectral acceleration, any kind of measure of intensity. And of course, very small levels of ground motion intensity occur frequently, and then very large levels occur infrequently. And if we have say we have just a site that's located here, this is our building, or our city, whatever, and we've got faults at different distances, there may be different frequencies that fall on that curve. So there are several steps in putting together a probabilistic seismic analysis, putting together a national seismic hazard model. The first is identify the sources. Where are all the earthquakes going to come from? Let's think about just a single site. We have different kinds of faults. We may have areas. We may have background seismicity. All of those are contributing. We need to describe the distribution of magnitudes that can occur on those various sources and the distances from our site. We need to describe the ground motions that will occur given those earthquakes for various levels of magnitude, various distances, and how much acceleration are we going to get from those. And then finally, we can assemble that information together with its uncertainties in order to generate hazard curves. And then I'll show you later how we turn a hazard curve into a map. So let's think about the ground motions. This is the ground motions recorded for many stations in the 1999 Chi-Chi earthquake in Taiwan. This was at the time the very best recorded, by far, large earthquake that had occurred anywhere. Taiwan had invested heavily in modern seismic monitoring, and thank you very much. This transformed PSHA for the globe in terms of how well we understood strong motion. And you'll see that as a distance away from the fault, of course the fault was long, so this distance away from the fault, the acceleration falls off the distance in this characteristic kind of pattern here with quite a bit of scatter. And it turns out you can describe this scatter with a normal distribution in this log space. And this is what's typically done. Then if you can construct these normal distributions. If you want to think about what's the probability that you will have encountered shaking above a certain level, you can draw a line there, and you know, if you're far away, there's very improbable that you will have encountered PGA of 1. But if you're closer, a little more probability. If you're very close, quite a bit of probability that you'll have encountered that within this distribution. And this is uncertainty. This is actually scattered just from a single earthquake. These are good recordings. So the real earthquake makes a lot of distribution of ground motion. So I'm just going to show you a few equations here to kind of step through this. And those who are very familiar with these equations, you may object to some of the formats that I'm using here, but I think it'll be useful. So we want to calculate the probability of some intensity measure. Let's say PGA. What is the probability that it will exceed a level, 1G, 0.1G, whatever, given an earthquake of magnitude M at some distance? So the probability the intensity measure will exceed some value is the probability of that intensity exceeding that value given an earthquake at some magnitude and distance. And we have ground motion models that describe that relationship. We can also describe this as a rate, so that the rate at which this is exceeded, so that the rate at which the intensity measure is exceeded is the rate that the earthquake magnitude happens, given this other stuff, given a magnitude, given a distance. That source, that given fault, like the fault of the Chichi earthquake, was very long. It can produce earthquakes of various magnitudes. It produced one magnitude at that time, but in the future it might be a variety of magnitudes at various distances. And so we can sum these up, sum all the magnitudes, sum all the distances in order to get the rate at which that intensity measure is going to be exceeded. And that's just one source, that's just one fault, so we have to do one more sum, which is to sum all the sources here, and then all the math just stays the same. So this is the basic equation of PSHA. It's really just summing up everything you know. All the sources, making all the magnitudes at all the distances, at each of them with a rate for all the sources, and add it all up. At this point, this is just a bunch of bookkeeping once you've figured out what all those relationships are. And then, so that, if we do that for one magnitude and distance, we get a position on here, an annual rate of occurrence of a ground motion intensity on that plot. And if we do different ground motion intensities, it's a little less likely to have a higher one, a little less likely to have a higher one, and so forth and so on. Put them together, there's your hazard curve. If you have multiple sources, so that's the hazard curve for one source. That's the blue one, say. Here's another source. That's the red one. And then because these sources are independent, the probabilities can add, and we come up with a total hazard curve for our site. That's for one site. Now, we have many sites, of course. If you want to create a map, all you do is repeat this, all this bookkeeping, for every site in your map. You might want to do it at every 10th degree grid, which I think is what we do for the US map. And so we get different hazard curves for the different cities. These are for 4 different cities in the US. We actually do it for every point on the grid and put together a map. So choose an intensity level. This map is for a particular intensity level. Do this on a grid, and then assign a color scale, and then you're done. So it's a particular thing that we're interested in, how much we want it to exceed, or how much we are going to calculate that it exceeds, how often, and then you can make a map. So you can see that there's 2 pieces of this. There's the sources, and then the ground motion given those sources. Let's first talk about the sources. We call this an earthquake rupture forecast, or a source model, and it comes with several different elements. First is the fault models. Where are all the faults? Deformation models give us the rate at which there's the slip rates on those faults, or the moment release rates on those faults, and those moment release rates have to be satisfied by earthquakes over a long period. So earthquake rate models then calculate how many earthquakes of what magnitude does it take over the long term to satisfy that moment rate. And then what is the probability in some time period that earthquakes of certain magnitudes will occur. Typically for PSHA, National Seismic Hazard Models, we're looking at long time periods. We're looking at earthquakes with long recurrence intervals. We consider those earthquakes all to be independent, and that allows us a whole lot of simpler math by just saying this is a Poisson process. These are independent earthquakes. We can easily add up the probabilities without a lot of fuss and bother. There's other ways to do it. You can put in time dependence, you can put in relationships between the earthquakes, dependencies and so forth, and it can get a lot more complicated. You can also, instead of doing all this, you can use models to calculate these things. So there's different kinds of sources that we consider. We consider single faults or fault zones, San Andreas Fault, etc. We look at the gridded seismicity. This is the measured rates of seismicity, and we can then extrapolate those up to higher magnitude to get a rate using a B value. We can also look at what we call fault system solutions. If you're familiar with USURF2, USURF3 models, the Uniform California Earthquake Rupture Forecast models, these look at what are the possible earthquakes that come out of the very complicated mapped set of grid of faults that happen to occur in California, taking into account the possibility that earthquakes may link up to make large earthquakes. And this takes a lot of energy and examination to figure out what are all the possible earthquakes, how can they all add up together to balance the moment rate, balance the long-term slip rate on all these different faults. Now, in practice, we know all of these things to some degree, but we know none of them precisely. And so we need to take into account our level of uncertainty. And the uncertainty in our knowledge is called epistemic uncertainty. This is theoretically some uncertainty that we can reduce if we learn more. But we need to take into account in our calculations. The way we do that in practice is through logic trees, by saying our uncertainty in something can be expressed by making a bunch of different choices. And for the source model, there's a whole bunch of choices they need to make, and you just break the problem into discrete choices. We've given a fault model. We have 5 different ways we use to calculate the slip rates on the faults. Each of those is assigned a likelihood, a weight, 0.26, 0.32, 0.02, etc. For each of these branches, there's a choice of the scaling relationships. For each of those, there's a choice of B value for the large earthquakes. For each of those, there's a choice of how you deal with the paleoseismic data for the segmentation model, et cetera, et cetera, et cetera. Same thing for the ground motions. We use several different models. We assign weights to them. For each of those, there's different choices about how you handle basins, how you handle basin depth, how you handle uncertainty, and so forth. So the calculation process, I said it was a lot of bookkeeping. It's a lot of bookkeeping because you run through every single one of those branches. Each path through the tree, comes, add up multiply all of those weights. The weight, the weight that comes out at the bottom, you're going to get a probability and a weight. And that distribution then creates the point on your hazard curve. So we did that for the US. We just completed a 6-year process to update the seismic hazard model. 6 years because that building code process that I showed you, that cycle through the 5 documents, that is updated every 6 years. And so if you're interested in this, you can go to our website. You can just Google that. On the website, there's a complete description, and I do recommend, whether or not you care about the hazard in the US, I recommend it because this is only the start of a long list of publications that describe the model and all the model elements. And together, this is a really nice compilation of the state of the science. What is it we've known? What are we using? And what are the opportunities for going forward? And this includes reviews by several review committees who put out an idea about, what are we confident in? What are we kind of shaky on? And what we say just is not ready now, but might be ready later. And this is where your science can come in. So, as you've seen, there's a lot of bookkeeping involved and a lot of elements to this, but in fact, they're actually pretty basic. We have fault slip rates, we have moment balancing, we have simple rules for putting the faults together, we have smooth representations of historic seismicity. We don't consider induced seismicity because that's a time-dependent process. We use weights for a logic tree that are the same everywhere. We're ignoring clustering, we're assuming the sources are independent, and we're using a simple Poisson recurrence model. And then there's a bunch of assumptions that are quite simple also for ground motion models. All of these are pretty basic. It looks like a lot of rules, but it's pretty basic. The science that you do can contribute to improving every single one of those. This is where we need to be going in order to improve these models. And we really need to improve these models because the uncertainty is really substantial. And uncertainty drives cost, as I'll say. Consider just for Salt Lake City, this is the hazard curve for Salt Lake City. And at this particular level of annual frequency of exceedance, this is the mean. This is, and then this is the different, what is it, 5th, 15th, 50th, 85th, and 95th uncertainty. Look at the spread of accelerations from 0.26 G to 1.1 G annual frequency of occurrence there at that small frequency. That is a 4 times difference. Imagine being an engineer and you're tasked with designing buildings that are not going to fall down in the next 50 years. And I'm going to tell you, well, the ground motion is going to be somewhere between 1/4 G and 1.1 G. That's a tremendous challenge. The more we can drive down these uncertainties, the more certainty we have in designing our structures to be safe. And if this is very broad, you have to take this into account. It's not a high likelihood, but it's possible. And we don't want to, if you're an engineer, you don't want to risk that. And if you're designing engineering policy for a country, you don't want to risk that. And if you're an insurance company, you have to plan for that. If you're insuring, you have to have your reserves and you have to charge your customers in order to be able to insure against that. So reducing this uncertainty or changing the mean, all of that has a tremendous amount of effect on insurance, on cost, on engineering, on everything, safety. So I'm going to go a little fast here through this next bit, just saying that just some examples of some of the things that need work. We have in the Western US so many faults, so many well-mapped faults that are close enough together that they could fail together. This is all pink because all of these faults are close enough together that any of them could fail together. End to end, you could make tremendous big snaky ruptures. And so we have a whole set of science in trying to figure out which ones are really possible, and if so, how do you figure out what the rates and magnitudes are on them? Induced seismicity, right now we're not considering it for the long term, but this is an example of one of many kinds of time dependence that are in hazard that we wanted to take into account. In the central US, this is much more hazardous than the background earthquakes. And in fact, we did this in the USGS. We put out 3 one-year hazard models, basically using the same mechanics as PSHA, but taking into account the rate of recent seismicity that was being driven by induced seismicity in the Oklahoma region, for example, to show that there was a higher hazard. So there are opportunities to improve these models, of course. One is to look at time dependence, to try to close this gap, looking at all these different kinds of time-dependent processes. Ultimately, where we'd like to go is to have some kind of a complete earthquake forecasting model that consistently spans all of these time periods and allows us to ask questions about short-term hazard, long-term, and so forth from a consistent view of the Earth. Looking at the ground motion data, again, going back to Chi-Chi, we talked about there's a tremendous amount of scatter, even for a single earthquake. And there's 4 different earthquakes shown here, but each one has a different symbol. You can see there's a lot of scatter there. And this is the kind of data that the engineers have to work with when putting together these ground motion models. This is the distance from the recording and the moment magnitude of the earthquake that was recorded. And there's a lot of data over here at long distances and low magnitudes. And there's not much here where it really gets into the large magnitudes and the close distances, which is where the buildings tend to fall down. And so this is where we use models to fill the gap. And there's a lot of work in here. For example, the Seismic simulation model that has been generated for many years out of the Southern California Earthquake Center Consortium. And you can see, just looking at hazard curves here, you don't need to see the details, but these are 2 popular hazard models, ground motion models in use. And here's what you get from Cybershake for Whittier Narrows. This is a location with a deep sedimentary basin. showing that if you take that basin into account, it can make a tremendous difference on your expected ground motions. And of course, Ioannis and others here have shown us that there's a tremendous amount of model development underway. And this is where all your science can come into improving these models and ultimately make them into improvements. I can give you I can send you the picture. And so your science can make a difference here. Your science can make a difference, but it takes some work. All of this stuff takes a tremendous amount of work in examining it to make sure that it's really good. And so any change to a policy model like the National Seismic Hazard Model of the USGS undergoes extensive, detailed, rigorous science review of everything, of the models, of the branches, of the weights, of the commuting methods, and so forth. The earthquake rupture forecast was reviewed by a 19-member panel that met, 18 times, and generated a 60-page review that is one of those things that you can download. It's an excellent paper. One of the things that's taken into account in this kind of review is valuation. We can make better models, but is it worthwhile doing? There's a tremendous amount of energy, computation, and so forth that's required to improve models, to introduce model elements. Do they make a tangible difference? The logic trees are examined in great detail. Just looking at these branches of the logic tree, the panel asked the USGS to look at the contribution to uncertainty from each of these branches of every model. And you can see that the deformation models at the top have a lot of uncertainty that are being driven there. That's how you compute the slip rates. And also the segmentation models. If you don't segment the faults, it makes a big difference. And one of the criteria that we use is what's called best available science. And this is talked about by, in another one of the reports that's on there, a short report from our steering committee. These are the criteria for the kinds of things that we should properly incorporate into a seismic hazard model, including it being rigorous, that the data are available, the computations are verified, and so forth and so on. So again, all of this has to happen with this level of review. I only described the review for the first one. All of this gets reviewed. And you can imagine why the engineers would care, because they are putting their reputations and their community's safety on the line from these models. They want it to be demonstrated to be very good, very proper, and so forth. And so when new models are introduced and accepted, it takes a lot of time and effort, and it's for good reasons. The existing models do pretty well. As I said, the professional users and stakeholders, they're cautious, appropriately so, because it takes a lot of demonstration to say that your innovative, new, cool thing is better than these simple models. So there's a high bar for introducing science that underlie, for things that underlie public safety. So you have to stick with it. But it can be extremely rewarding, because if your science makes it into a building code, an operational forecast or something, that is really a crowning achievement. So I'm going to skip ahead a little bit, but I wanted to just make one more comment just as an illustration about this. Southern California Earthquake Center put a tremendous amount of effort into developing very sophisticated ground motion models that take into account what we know about source physics through ground motion propagation through ground shaking, including rupture deactivity and propagation along the source and so forth and so on. Tremendous amount of work. But how do you convince the engineers that something like this is better than, single degree of freedom, with an earthquake, with a Chi-Chi earthquake shaken at the base? You have to do that through a lot of conversation and a lot of demonstration. And so in 2011, SCEC formed the Ground Motion Simulation Verification Group. This brought together the scientists who were creating these models with engineers who would be, these are typically academic engineers, but ones very connected to the whole engineering building code process, to talk about, okay, prove to me that this really works. Okay, I'm going to demonstrate this, so forth and so on. And I was watching this happen as an observer of SCEC, our program sponsors SCEC. And really, I thought that we really reached a milestone when this happened, in 2016. Greg Deerlane is a very well-respected engineer. He's at Stanford University. He's a member of the Academy of Engineering, and he's on these engineering committees that determine what gets made into the building codes. And when it came to 2016, he gave a talk at the SCEC annual meeting called Utilization of Ground Motion for Nonlinear Analysis and Design of Tall Buildings, in which he said, this stuff is actually valuable. This was really a demonstration that a milestone had been reached after years and years of effort, that a prominent engineer, one of the pillars of engineering design and acceptance, had said, okay, there's really some usefulness to this stuff. We should be using it. So that was a real achievement. Okay, let me leap ahead a little bit because I want to get to some things here. I'm not going to talk too much about earthquake forecasting because of time, but fortunately Jean-Philippe gave us a little bit of a taste of that. We can use simple relationships, our knowledge about Amori decay, Gutenberg-Richter relationships, to say something about, given a main shock, what aftershocks do we expect? The math is pretty simple. Statistical seismology, you use existing seismicity to define the values of a very small handful of parameters, and then you can make forecasts out into the future. And USGS now has deployed this as an operational forecast. After every magnitude 5 earthquake in the US, we put out forecasts starting 20 minutes after the earthquake and updating them periodically for a year. Given the likelihood of earthquakes of various magnitudes at various time periods into the future. So this is an operational forecast. These are probabilities. They're expressed in plain language, 1 in 200 chance of at least one magnitude 5 earthquake in the next month, for example. So we put out this information. Again, this is operational stuff. It's based on pretty simple models. It's based on standard statistical seismology, empirically derived parameters. The probability levels are pretty much entirely driven by either the fact that you had a main shock or that you've got a rate of seismicity that you're observing and changing. And because of this, the probability of having a main shock is almost, maybe 5% or less. You're never going to get a 50% probability of a big earthquake in the near future out of this. This is where we have possibility of physics-informed forecasts that could help us do better. And fortunately, there is actually because we need to have some certainty and some testing, there is a mature infrastructure, collaboratory for study of earthquake predictability. If you have methods of forecasting that you would like to test, there's methods for doing that. The tests are set up, the Python is set up, the Jupyter notebooks are set up, and so forth. So I encourage you to take a look at that. Now, the last thing I want to talk about in the last few minutes is application to real-world decisions, because this is where rubber meets road. We talked about that for the building codes. PSHA is, science, goes to models, goes to engineering design, goes into building codes, goes into public safety. That is a well-designed pipeline. But there's lots of other ways without, taking years to get your bit of science into a model, There's lots of things that you can do now. And I'll just give a few illustrations. One is, so FEMA. FEMA responds to earthquakes by sending a big team of people to help the communities respond. And they need to keep those people there until the hazard has gone down to an acceptable level. They don't know how long that's going to be, but they need to anticipate it. It's extremely costly. In Puerto Rico, we had a big earthquake sequence in Puerto Rico. FEMA sent 1,000 people to Puerto Rico, 1,000 people. And they wanted to know, how long are we going to need to keep 1,000 people in Puerto Rico? And so they asked us, well, how long is the sequence going to last? And you know, it's hard for somebody in FEMA's shoes to say, well, I'm seeing seismicity. I don't know how long it's going to keep going. I know that aftershocks taper off, but how do I make a decision, a concrete decision about something? And so they asked the USGS, and our statistical seismologists looked at these descending probabilities and rates of earthquakes and came up with a tangible rule for what would it be an acceptable lower level of seismicity to anticipate, and gave an estimate of how long that would be, and provided that to FEMA. So a concrete decision. Another example. An earthquake has happened, a lot of buildings are damaged. A lot of buildings have been red tagged, which means unsafe. This is what building inspectors do after earthquakes. They green tag, building's great. Yellow tag, it's damaged but occupiable. Red tag, don't go in it. But there's lots of reasons that you're going to have to go into a building. Retrieve possessions, do some shoring, and so forth. So how long to wait? A building inspector is not going to know that. A city official is not going to know that. But we can give them an estimate from statistical seismology, and that happened. And this was a little publication put out by Applied Technology Council many, many years ago now. And this is Paul Riesenberg at the USGS, a statistical seismologist, working with 2 engineers. And they put together just a little set of rules saying, if you've had an earthquake greater than 6.5, you can enter the building for 2 hours after 1 day. You can enter the building for 8 hours after 3 days, and you can go in for 24 hours after 8 days. Simple, clean, easy rule of thumb. This is a kind of very simple exchange that can be made. And in fact, we pulled together a workshop where we brought together a lot of different users and asked them what kind of aftershock information would be useful to you in making decisions. What decisions you have to make, what would be useful to you. And there's a nice report you can find in GRL, Field et al. 2016, that describes what are these different user groups, what are the decisions they make, and what can we do. And this is information we can provide without any new science. This is just stuff that it takes sitting down with them, deciding what they need, and how we can provide it. All right, now, I was going to talk to you about Parkfield, but I think if you don't know about Parkfield, ask me about Parkfield. Parkfield was an experiment in earthquake prediction and monitoring, but it was also an experiment in the communication of earthquake warnings to decision makers. And there was work done with the state of California to say, if we declare a D, C, B, or A level alert based on our expectation that the new Parkfield 6.0 earthquake is coming, the state will take actions. At the C level alert, they'll send a notification to fire stations. At a B level alert, the local governments will take some sort of an action and so forth. So we can generalize that, and I'm just about done. We'll generalize that to saying the scientists have information that we can provide. Hazard and risk criteria, we could define it as different levels for different kinds of earthquakes. The decision makers have decisions to make, not probabilities, concrete yes or no decisions. They have actions. Well, if we work with them, we can tie an action to that probability that we have on our side. It's a handshake, it's a handoff. And that can be very effective. But you have to do the work of talking to the stakeholder ahead of time. And we have to remember as we do so that our principles that guide this, as we have authoritative information, we need to share it. We are on the science side. The users have information that they need and decisions they made. We don't make those decisions, right? They make the decisions. We provide the information to help make the decisions. So this is this hazard risk separation principle. So I'll conclude here with just 6 main messages. So there are forecasts, short-term and long-term, that are really the key to how we achieve risk reduction. There's tremendous opportunities for putting your science to work in doing this. As you do your research, at least think about these pathways, about how your science can inform risk reduction. or participate in the process. It can be very valuable and rewarding. It can take surprising amounts of time, so there's a lot of perseverance that needs to be understood. You have to be patient. But there are also opportunities even without going through that. Just take what we do know already and put it into work with these simple decision support tools. So get to know the users, get to know the decisions that they need to make, and the tools that they use and the factors they consider. And thank you for helping make us safe.
Thank you very much, Michael, for that very nice description of why what we do actually matters. Yeah. Is there questions in the audience? Yes.
First of all, thanks for this sensation that to be in a playground and then the adults come in. Do you think there is some part of the scientific community that is not here and should be here while we are talking about earthquakes?
Well, this is an earth science community here. There's other pieces of the community that really are important for us to work with. There's geotechnical engineering, for example. There's civil engineering. We can get farther and farther, but geotechnical engineering is very close to what we do. We haven't talked here about, we've been talking about the earthquakes themselves. We've not been talking so much about earthquake impacts to buildings, to ground failure, faulting, so forth. All of this work, fault creep, after slip affects buildings, right? Napa earthquake, there was a tremendous amount of hazard because there was a lot of after slip following that magnitude 6 earthquake, just as one example. So there's lots of others who could be here. And then of course there's all the stakeholders and users, and just a single well-spoken, articulate, and brave stakeholder sitting in a room like this can make a tremendous difference by saying, either tell me why that's important, or I can see why that's important for a practical reason that you may not have thought of. So.
Thank you for the overview. I was wondering what are the largest source of uncertainties in the source model, and how earthquake science, the current efforts should be directed to reduce those epistemic uncertainties.
Yeah, that could be a long discussion, but I'll point to a couple of things. One is the time dependence. At least the way what I described was a long-term time-independent model, the National Seismic Hazard Model. That's assuming that nothing's changing over time, and we can take an arbitrary 50-year period of time, we typically do because that's a building lifetime, and we can assign a probability to that. We could do a 10-year or a 1-year and so forth. It turns out that because there are assumptions made about the independence of events and about the durations of the hazard calculation interval relative to the rate of the earthquakes, that looking at high levels of exceedance probability, that the model doesn't do very well. So in order to say, the maps I showed there were, say, 10% probability of exceeding a ground motion in 50 years. In other words, turn that around, what's the ground motion that will be exceeded on average every 500 years? Well, if I want to know the ground motion that's going to be exceeded in a decade, I need a much more sophisticated model. That's where I need time dependence, I need clustering, I need independent earthquakes to become dependent, and so forth. So that's a big area. And if you look at some of these papers that I pointed to, there's a lot of description about that. So I encourage you to do so. So time dependence is one huge area. And then another is how to deal with fault networks. How do you deal with faults that have changes in slip rate around their length? You only have one earthquake in history. How do you extrapolate that to the possibility of earthquakes at lower or higher magnitudes? How do you know what those rates are? How do you know that two faults that come together like this or like this do or do not connect? How do you know whether an earthquake will propagate through a patch of creeping fault and come out the other side? These are all very important, but we have very little information about them. So this is where work can be done.
There you go. Thank you for the talk. I have just one comment or question. A few months ago, there was this earthquake in Japan, and there was this alert that was
what do you think if this should be like systematically implemented, like in the US,
So you're talking about the report that was put out?
Because there was this earthquake, right? There was a potential foreshock.
Right. Yeah. So what happened in Japan is, in fact, this protocol had just been established, I guess, a few months earlier, which is the Nankai area in southern Japan has the potential for a devastating earthquake, magnitude 8+ earthquake. And they put into place a protocol in which if there was a magnitude 7 earthquake anywhere inside this contour, that a message would be sent out to the population saying there's an increased probability or an increased likelihood of a magnitude 8 earthquake in the following week. So it's a foreshock advisory. They didn't assign a specific probability to it, but they did provide some numbers about this has happened 6 times in the last century out of this many earthquakes, blah, blah, blah. It's about 0.4% likelihood. So 0.5% likelihood, 1 out of 200, 1 out of something like that, likelihood that in the next week there's going to be a magnitude 8 earthquake. That is a much higher probability of a magnitude 8 than in any average week. So this was significant. The question I think many of us around the world are asking is, was it effective? Did it communicate well? It's very difficult to communicate small probabilities. I mean, if you call 0.5% small, I think Warner Mazaki, who's a colleague at INGV, or was at INGV now in Napoli, has pointed out that if you were told there's a 0.5% chance that the earthquake or the airplane you're about to enter will fall down out of the sky, you would never get on an airplane, right? Right. So is 0.5% small? Is it large? That's a personal evaluation, and that's where I get to this idea of talking to stakeholders. And this is where we're very interested in learning from the Japanese experience. They put this out, they put it to a tremendous number of users. What was the reaction? Did people take action? Did people appreciate the information? Was it communicated in an effective way? Because we all want to learn from that. They set it up so they had that out in 2 hours. No decision can be made in 2 hours by a bunch of scientists sitting around in a committee. So this has to be ready to go. It has to be pre-written. You just put in a couple of numbers and you send it. This was a great experiment.
Just before Ioannis runs out, he has a question.
Thank you very much for the very interesting presentation. It structures thinking, actually. I had a question related to induced seismicity because you talked about earth scientists, engineers, policymakers, but I would like to put into the question our beloved, profession of lawyers. What happens if I have designed a building with a specific hazard curve, so following the building standards, the building codes, and there is a reservoir and there is an exploitation of induced seismicity that increases the hazard? My building won't be any more satisfying the initial requirements and specifications.
That's right.
Is there legislation? Is this somehow thought in the?
So this is where it comes down. This is where it becomes policy and politics, because this becomes a policy decision by local governments or state governments on how to address this changing hazard. Because you're right, the hazard that is being faced by the structures is not the hazard they were designed for, and it's. Induced seismicity is a funny kind of hazard because earthquake hazard in general, despite some of the work that we have, thinking about earthquake control, we don't have a lot of control on it. But induced seismicity is different. And here is where there was a lot of churn in the US about induced seismicity, as there has been in Europe, about should we make a policy decision that then lowers the hazard because our structures are not built to this. But at that point, it's the scientists and the engineers can help inform that decision, but the decision is ultimately a political one.
But does this activate any liabilities of the operators in the sense of a legal sense?
That I'm not qualified to say. I don't. Maybe somebody in the room has dug into the questions of operator liability. I think the easy answer is that regulation, if they're working within regulation, then they're covered. But so there's a risk that they have for courts. There's a risk that they have for insurance, but then there's a business risk. In fact, When induced seismicity started coming up in the central US, we started talking about, well, we typically think sort of magnitude 5 is the magnitude at which you start having a risk to structures from earthquakes. And we don't need to really worry about them so much. They're just a nuisance. Magnitude 3 earthquake that's widely felt in the middle of Oklahoma City is a business risk. And so it becomes in the interest of the industry to regulate themselves, or for the state to regulate them, to reduce down the number of felt earthquakes, because a felt earthquake is a business risk. It's a different kind of risk.
Thank you very much.
So, Anna, you have a question? Or?
Yeah, I had a question relative to also Jean-Philippe talks. He showed that using geodesy to do seismic hazard prediction, PSHA, but can be very useful, and it's true in areas where you have high rates of strain. But do you think that in fact in areas which are continental interiors, it's pretty difficult because you have both a lack of earthquakes and old earthquakes and historical earthquakes, and you also have a limitation in terms of strain rate computation.
Yeah.
So how do you think that do you think that geodesy could help at all?
Well, geodesy definitely does help, and in fact it's incorporated already to a limited extent into these models. Those deformation models that I showed in the western US that are taking combinations of geologic data and geodetic rates from GNSS and putting them onto calculations of what the slip rates are in the fault that satisfy that rate field. It's much more difficult. I'm sorry?
The western US is deforming fast.
Yeah. It's much trickier in the slowly deforming areas, of course. And if we're doing our jobs right, and I didn't talk about this very much, but in terms of uncertainty, if we're doing our jobs right, we should be fully accounting for all the uncertainty. Remember how I talked about that's one of the jobs of PSHA, is to take into account all the sources of uncertainty. And that's how we use logic trees. And the second corollary to that is, if we do some good science, we reduce the uncertainty, right? That's not really been our experience over the past decades, because we've started with very simple models with underrepresented uncertainty. We've thought that they were much more certain than they are. And then every time we add more complexity to the model, it becomes more uncertain. Well, that's backwards. We really need to think out of the box. What do we truly know? And if we're looking at a model of the US, there should be much less uncertainty on the West Coast, where we have high earthquake rates, we have paleoseismic rates, we have a lot of geodesy, we know a lot about the earthquake cycles. In the central US, there's be tremendous amounts of uncertainty. And in fact, in the USGS, we have arguments about where should we be putting our energy. Should we be putting our energy into areas where the seismic hazard is high, because it's high? Well, those are also the areas we've studied the most. Should we be putting our energy into the areas that have relatively low seismic hazard, but tremendous uncertainty that might be reducible? And there's good arguments to be made that investing in the science, in the geodetic monitoring, which has to be long-term in order to make a difference and so forth, in the areas of low hazard will pay off in the long term. But we have to make the investment.
All right, so I'm sorry, we really have to go for lunch, otherwise they will close the room.